Okay, here we are. Good morning, everybody, and welcome to all our students and experts to the 5th edition of this TREX virtual school on Quantum Monte Carlo codes. The school is brought to you by the School of Advanced International Study in Trieste, the SISSA school, the PSYCH network, and the TREX project. The TREX project is the targeted center of excellence for the community of quantum chemistry and has been funded by the European Commission. It started its activities in October 2020. And it aims to develop efficient and portable Quantum Monte Carlo libraries and to feed a stronger community of Quantum Monte Carlo users. And that's the reason why we organize also training activities and summer schools, such as the one that you are attending today. So as you know, the school that you sign up to will last the entire week. So we start today and will continue across the week until Friday the 16th. The program today will be opened by Sandro Sorella, professor at the SISSA school, who will give you an introduction about the school and the official welcome to all of you. Then during the morning, you will also meet Michele Casula, who researched at CNRS, who is one of the lecturers of the school. And just after the lunch break, you'll meet Kosuke Nakano, professor at SISSA, for another lectures of the school. The program, as you can see it on the screen, is also available online on the TREX website. So we'll break a little bit around 10:30 for a coffee break, and then for lunch at 12:30. Then we'll convene again at 1:30 for Kosuke's lectures. And then, as you know, the afternoon will continue with some hands-on sessions, which have been reserved to 24 students only due to issues of capacities more. So we couldn't allow you all to join, unfortunately, and that's why a selection was in place. The hands-on tutorials will run on Zoom, so the same link as you have here, and we'll have 8 breakout rooms. We'll provide you some further instructions later on before the starting of the hands-on session on how to join. You see here the names of the tutors for these breakout sessions, and each room is assigned to a tutor's name. So find yourself in the list, but don't worry, we'll guide you through the process later on in the afternoon. There might still be some changes to this agenda and to the organizations of the rooms as you've seen them here, but we'll present this structure again to you after lunch. So don't worry too much about that. So some housekeeping before we start. So the event is recorded entirely, so the morning and also the hands-on sessions. And this is done for dissemination purposes. So we want then to showcase the plenary sessions later on online, while the hands-on tutorials will be only shared for training purposes with the participants. All the presentations will be available on the website after the event. So your microphones are all muted. This is for ensuring a better quality of the streaming. And the same is for your cameras and the videos. But I mean, if you have any questions or burning needs, I mean, to speak, feel free to use the chat of Zoom, and the lecturers and tutors will accommodate your needs. If you have any troubles with Zoom, if you don't see links, feel free to or use the chat or contact the TREX team at info@trex.com. coe.eu. And the same if you have any troubles with the video. The tutors and lecturers have set up a Slack channel to continue the exchanges and the communications within this group. So feel free to join it. You should have received details in an email before this event. If you haven't, don't worry, we'll send this again. And this is done also to ensure your questions are asked and are addressed even after the time of the school. And before giving the floor to Sandro, I like to show you once more the opportunity that we launched in the framework of the TREX initiative of this poster competition. So we invite you to submit a poster. We have extended the deadline, so your posters will be welcome until the 30th of July. So you have time also after this school. And the posters will be evaluated by a committee, but also by public voting that we will hope through the TREX website and via our social media channels. We'll evaluate this, and then the technical committee will then evaluate the scientific appeal, the relevance and clarity of the message, the technical content, and also design visuals and attractiveness. And we have some nice prizes for the best free posters. So take this chance. And with that, I leave the floor to Sandro. So I wish you a very pleasant week ahead. And thank you very much for joining TREX. Sandro, the floor to you.
Thank you. Let me. So I should share my screen. So welcome everybody, and thank you for joining this school. Actually, as you know, the story of this school was planned to have a normal event done in SISSA, in presence, with a normal lecture. But unfortunately, you know, the situation due to this COVID restriction is recovering, but not enough to have the school in presence. So somehow this is some kind of experiment that we hope will be successful, that all the teachers have to do. They would like to have a blackboard. We will try to have to work with iPad and things like that. And what I saw, despite this, we were very happy that we received several applications. And I'm sorry that the limitation of the computer resources that we have does not allow us to have to give you the opportunity to follow all the tutorials. But in case there will be some cancellation, we will be happy to include some people. So be aware that not necessarily you will have a chance also for this, especially if you follow the lecture. This is what the main introduction, this school was also luck because we had several sponsors, CKA, SISSA, and TREX itself has given us a lot of support, but we cannot use because we cannot pay your hotel if you are in Trieste. I hope one day we will have this school in presence. So certainly, if this event will be done again in a couple of years. So And I hope in a couple of years we are far from any trouble for this COVID restriction. So what I have to say, I don't know, I just share one slide and with maybe a long discussion about the points. So you come here, I hope you know something about Quantum Monte Carlo, otherwise, okay, even if you don't know, you will learn here what is Quantum Monte Carlo. And the main thing that I want to discuss now, in few words, what you are supposed to learn here. So this is, we are talking about a wave function approach. So you have a wave function you believe is a good representation of your electronic ground state, and you try to understand the physics with this wave function. The main thing is that we can consider correlated wave function, not only mean field wave function like is usually done in density functional theory. And the main approximation is to say that we include the electron-electron correlation in this simplest form. So basically, we look to the pairwise distance between a pair of electrons, and we try to represent the correlation in this simplified form. You have to, and this is called, you will listen several times, this Jastrow correlation, probably you have already heard. This type of correlation is very successful in electronic system, because basically if you start from the simplest beam field, that is the R3 Fock, you are able with this simplified version of the electron correlation, you improve the accuracy of the mean field by an order of magnitude, basically. On top of that, you have also the so-called diffusion Monte Carlo. That is a projection technique that, in principle, allow you to get exact ground state properties of a given system. Sometimes I say sometimes exact because you know, in Monte Carlo, the exact solution is related to the so-called solution of the sign problem. And the solution of the sign problem is one of the open problems in computational physics. I think it's, if you solve this, you have $1 million. It's one of the fundamental problems in computations. And so we have to do some approximation. So this diffusion Monte Carlo is exact for two electron systems, like the helium atom or the hydrogen molecule. This is not trivial cases because we will see in the hands-on that basically no mean field method can capture the qualitative property of this system in a satisfactory way. And in general, this further improves the accuracy, so you will get another factor of 4 or 5 more accuracy with respect to the 90% that you already have by the so-called this extended variational, correlated variational framework. Then this is basically what you have heard and is standard. So not only in this school you will have the possibility. I mean, in the code that we will use in this school, that is TurboRVB, you will be able to apply this technique, but there are several packages in the market, like QMC Pack in USA, Casino was also very popular in Europe. And I don't know, QWalk, and there are several that do this job. So what we want to focus in this school is that on this suite of codes, TurboRVB, that can do the standard thing, that is applying diffusion Monte Carlo and improve the mean field with just of correlation, but can do also something more. Than the standard, we compared whatever the standard means. First of all, this suite of code, you don't have to know other codes. So if you learn this, you can do your homemade mean field, which is obtained by density functional theory with LDA or local spin density. So we have a tool inside this suite of codes that allows to you within a given basis, within a given pseudo potential. I mean, this name probably you don't need to know what does it mean, but it's more or less the standard thing of a mean field, density functional theory. And you can do this calculation within the same framework with which you will apply the density functional, the diffusion Monte Carlo of the so-called variational Monte Carlo when you include the Jastrow to your mean field. I emphasize that, well, let's say that I have to talk about the story of TurboRVB. TurboRVB started almost 20 years ago, was the PhD thesis project given to Michele Casula, that is one of the lecturers in this school. And basically, I had a lot of experience in lattice model calculation, where I appreciate this approach to use electron-electron correlation in terms of Jastrow factor and diffusion Monte Carlo to improve upon them. But what I have learned until 2000 from this lattice model was that it was really important to do the optimization of both, so to minimize the total energy of a given system, both the Jastrow part and the mean part. The usual path in standard codes is to take the mean field part by another code, so another, I don't know, Quantum Espresso or Abinit or whatever DFT code, and then take this mean field, do not change, include the Jastrow, and apply the diffusion Monte Carlo. This is the standard somehow. That I don't say that is bad. Actually works several times, probably for your case, and we have also experienced that in our long experience, 20 years, in several cases, this standard path works. But there are several systems, especially the more interesting thing that I am interested, for instance, cuprate superconductors, iron peptides, also recently this tilted bilayer graphene, and several systems in which correlation is more subtle than that. And what, again, I emphasize, I have learned from lattice model calculation, when the correlation matters, the mean field part can be completely different after you optimize together with the simplest form of the correlation. So for instance, you take the Hubbard model, if you optimize, if you take the R3-4, this is a free electron Fermi gas, so has no superconductivity. But if you optimize, and this is a repulsive model, if you optimize the energy of the mean field part together to the electron correlation, you get that this model can sustain off-diagonal long-range order, so D-wave superconductivity in the ground state. So it is crucial sometimes to optimize both ingredients together. And this is a very, very difficult task that we started several years ago. And we hope to teach you, at least in some cases, in this school. That will be, well, of course, we cannot, actually, this is a long-term project. I would say that still we have the problem that the Monte Carlo is a very heavy technique, especially when you require to do the full optimization of the mean field in presence of the correlation term. The fact that it is very costly is well known. So if you apply DFT, you take, I don't know, the ground state of 100 electrons with your laptop. So the approximation, the mean field corresponding. If you do 100 electrons with Monte Carlo, you have to use the supercomputer. And we will give you a flavor of one of the most advanced supercomputer that is now in Cineca, is the Marconi 100, that you will allow to use this supercomputer with 2 nodes, with at most 2 nodes. But it's already much better than your laptop. Especially because this supercomputer exploit also a very recent progress in the computer performances, that is the acceleration given by the so-called GPU. Some of you may have known or not this recent advance. And so what we are somehow seeing in recent years is an enormous progress of supercomputers, and you can do a run with several processors doing the same job. And you will see that if you exploit this big advance in computational resources, the Quantum Monte Carlo is not, begins to be, you can do the calculation in a time that is reasonable. So you will see that in the tutorials that we will see, you will not take much to have the almost an exact representation of the ground state of small molecules with a couple of minutes, not more. So this is also the reason why we got this important project financed by the European community. This the main this is TREX, targeting real chemical accuracy at the exascale, and the main letters that is exascale. What does it mean, exascale? It means that in the near future we can do 10 to the 18 flops operation in 1 second. So this means, and this thanks to this huge progress by the supercomputer. And once this is achieved, we believe, since until now Monte Carlo is restricted to a very small community, I think the Monte Carlo will be more and more used, because really we can do successful and very accurate calculation controlled by the variational principle, because this is a wave function approach, with a reasonable time. So that this is the main advantage. So this is what I want to say, and TurboRVB is prepared to do this tough job that will not be so tough, so to have very accurate wave function optimization, very special mean field. You will see that not all the mean fields that you know are simple Slater determinants, and it will be, we hope, used by several people in the near future. So I thank you very much for your attention. I spent too many words, and it's already time to give the floor to Michele Casula for the first lecture.
Thanks, Sandro. While Michele joins us, there is a question in the chat by Varnajan, and maybe I'll read this loud, and I'm sure this will be addressed later on, but the question is, can we install TurboRVB on our computers, I think?
Oh, this is a very important question, actually, I forgot to say. This is TurboRVB will be, thanks to this project, will be an open source code in 2023. We are working, this is because we have to do a reasonable manual and something that can be used user-friendly. But after this school, if you follow this school, you probably will have enough knowledge of this code that you can download the nowadays private repository. That this is in a SISSA repository, and we will be happy to include your name in the. So at the end of the school, you send an email to the organizer or in the Slack channel that we have prepared for you, and we will be happy to include you in the users that are allowed to download the TurboRVB. Okay, thank you for this nice question. I stop sharing.
Yeah, Michele, feel free to share your screen. Yeah.
Hello, everybody. So thanks for joining us for this first day of our school. This first day, after this nice introduction by Sandro, will be devoted to some remarks or short introduction to the probability theory and the way to sample a given probability distribution. Later, when we'll be done with this part, I introduce you basically the main technique of today, which is the variational Monte Carlo. So just a few words about myself. I'm a CNRS researcher located in Paris at Sorbonne University. And as Sandro mentioned to you, I joined this TurboRVB project since the beginning, so I had the chance to follow the progress and the first years of this kid who grew up at the end, and now I think is ready to be released in a more official way and also for a wider use worldwide. Okay, so that's the outline of this first lecture. The first part will be about the ab initio Hamiltonian, which is our, if you like, reference theory we'd like to solve. After that, I would like to talk about, always as introduction, about the sort of supremacy of Quantum Monte Carlo. By supremacy, I'd like to mean those aspects where Quantum Monte Carlo is really the theory, the method to use to solve the ab initio Hamiltonian. And then we'll see the main reason why we use Monte Carlo, namely, we'd like to integrate an integral, which depends on many variables. So it's a multidimensional integration. And by having this as target, we need to deal with a probability distribution. And so then I'll introduce you all the features and all the properties of a given probability distribution, how to sample it properly. And finally, that's the last part, as I told to you before, that's the variation of Quantum Monte Carlo. It's the application of all the previous ingredients in this technique, which is the most simple one among Quantum Monte Carlo methods, but it's the most important, if you like, in terms of also understanding of what Quantum Monte Carlo technique is. Okay, so this is the ab initio Hamiltonian. That's our, if you like, theory of everything. So we'd like to solve this because that's the Hamiltonian which describes the low energy physics of condensed matter. And basically it's based on fundamental interactions, which is the Coulomb interaction between electrons. So that's the term in the middle here. And then we have also the interaction between electrons and nuclei, which is the last term in the Hamiltonian, in the first equation. And then, of course, as we deal with a quantum system, we have the quantum kinetic term, which is the first one. So basically, our systems are made of electrons and ions interacting through the Coulomb interaction, and the behavior of electrons and eventually also the ions is quantum. So with this Hamiltonian, we are able to describe the low energy properties and chemical reactions, conductivity, transport, also thermal conductivity as well. So we have all the properties we can experience in our everyday life regarding materials, compounds, condensed matter in general. So we have a reference theory, we have a well-defined theory which describes all these phenomena. The difficulty is to solve it. And so that's the equation here, H psi equal E psi. So that's the Schrödinger equation for the ground state of the system. So we'd like first to study the ground state, but eventually also excited states, of course. The ground state itself is a challenge. And this basically is already an important solution of the many-body problem. So our goal is to find both the energy and eventually the wave function of this problem. And we have actually several methods which are able to do that. So it's a hard problem to solve. It's for basically in the majority of cases, it's not solvable in an analytic closed form, but there are different approximated ways to tackle it. And basically, those ways have been developed in the last, I would say, 100 years since the dawn of the quantum theory. So the first method used to solve the Schrödinger equation is density functional theory. In density functional theory, you replace the complexity of the many-body wave function here, psi, which depends on n electrons of the problem. You replace this full psi, this full function, which depends on 3n coordinates, into just one function, which is the density, which depends only on 3 coordinates. So it's a tremendous simplification of this problem here. In principle, the relation between the energy and the density obtained through density functional theories is a basically a relation which gives the exact solution of the Hamiltonian. So at the end, you would get the exact density and the exact ground state energy. The problem is that to get this exact density and exact energy, you need to know an exact functional. So this exact functional is not known, and it's usually replaced by approximated exchange correlation functionals, constructed, built upon some physical intuition or some parameters. So this approximation makes the theory, of course, not exact, but the solution can be achieved, is doable, and the scaling of this kind of family of methods is n squared log n, usually maybe also n cube, and despite being approximated, this has been widely applied in material science, condensed matter, and quantum chemistry as well, and with, I would say, very good results in general, but also with some failures, and is usually a theory used to solve large systems thanks to this scaling with a system size. I recall you n is the number of electrons, if you like, so is the number of the size of our system. So you can solve large systems with a decent quality, but with some failures as well. So another family of methods, which is the second one here, it's basically the family of post-Hartree-Fock methods. So Hartree-Fock is again another theory, which is given by, if you like, the solution where you replace this many-body wave function psi r1 rn by a single z determinant, and you're going to see this with Sandro tomorrow. What is a single z determinant? So if you make a simplification of this general form psi r1 rn, you get the Hartree-Fock theory, which is the if you like the simplest antisymmetric form, and that's not enough, of course. It's a rough approximation, and so quantum chemists try to go beyond Hartree-Fock and developed many, I would say there is a long list, many post-Hartree-Fock methods, like a couple cluster, multi-reference, set consistent theory, CI, configuration interaction, and so on. So you have a long list of methods which try to go beyond Hartree-Fock, and all these methods are based on in the improvement upon the wave function psi, this wave function here again. So you make basically a guess for the true ground state or eigenstate of the Hamiltonian, and you try to solve for this guess and to get the eigenstates. So this guess is based on the expansion in many determinants. That's usually the idea. So you go beyond Hartree-Fock and you expand psi on a basis set, which is a complete basis set for the Hilbert space. So the Hilbert space is a space where psi lives, and the determinantal space is a complete basis set for the Hilbert space, and you expand psi in terms of many determinants. How you expand this wave function, in the way you expand this wave function, this will define the type of method you're going to deal with. And usually the expansion is done on a single electron basis set, single particle, which is usually Gaussian form, because in the Gaussian form, all relevant integrals like 2-point integrals, Hamiltonian integrals are analytically evaluable, can be computable analytically. So these post-Fock methods are very accurate for small systems. In particular, for small system, you can reach also the complete basis set expansion, which is the CI expansion. So in principle, you can get the exact result. But the drawback, the main drawback, is that the scaling of these methods is CI, for instance, is exponential. So you get the exact results for very small systems, but as soon as you study larger and larger systems, the quality of the approximation, the quality of the method decreases, deteriorates substantially, just because you should make some approximations to make the solution affordable. And so you have to renounce about a complete basis set, and you should cut your expansion in different ways. And by cutting the wave function in different ways, you make approximations, and while the scaling is still substantial. So those methods have scaling properties which range from n to the 4th power to the exponential cost. So you have a very slow convergence in terms of the main determinants expansion, and the accuracy deteriorates very fast on the system size, although you get benchmark results for small systems. And then there is the third way. So Quantum Monte Carlo techniques. Those are still wave function based methods, like the post-Fock methods. But instead of expanding the wave function in zeta determinants, you deal with so-called explicitly correlated wave functions. Okay, and so we're going to see the form of this wave function later. Yes?
There is a question on the chat. If you can do some examples, what are the failures of DFT?
Yeah, so I'm gonna. So the question is now if you hear Sandro. I think Sandro, you are muted. So there is a question on the chat asking what are the failures of DFT. So I'm gonna show you some failures later. Okay. Yes. So Quantum Monte Carlo techniques. Again, wave function based methods. So we're going to see the form of the wave function. So it's a way of including correlation. So it's a way of going beyond Hartree-Fock in a sort of clever way by condensing the correlation in some compact analytic form. And the drawback is that then, we're going to see this later, the multidimensional integrals necessary to solve the Schrödinger equation are no longer computable in an easy way. So we should resort to a stochastic approach to compute these integrals. Nevertheless, this is basically if you like, the third way, which is very accurate for both small and medium-large systems. It's more time-consuming in general for, if you like, small system compared to deterministic methods, and that's due to the stochasticity behind it. But it keeps the accuracy very high throughout the scaling with the system size. And so it's basically the benchmark system for medium-large, the benchmark theory for medium-large systems. Because while keeping the accuracy high, it also keeps a very good scaling with the system size. And so we have the n cubed to the n4 scaling, where again, n is the number of electrons, so it indicates the size of the system. And so basically you get into a region, if you like, of in the space of accuracy versus scaling, where Quantum Monte Carlo is really the technique to use. And indeed, it has been used since the 80s to provide the best solution for the electron gas problem, for instance. So the electron gas was one of the first problems solved by Quantum Monte Carlo. And the electron gas problem, so it's the Hamiltonian we have seen before, but with the difference that you don't have ions, you have basically a homogeneous background. So if I go back to this Hamiltonian here, so instead of this term, you still have the electron-electron interaction. Instead of this electron-ion interaction, you don't get ion, you don't have ions in the system, but you have a homogeneous background, neutralizing the total charge. And that's basically the Gellium model, if you like. So why is so important? Because the Gellium model is the reference model to build density functionals. So if you like, when you run a DFT calculation, which is the first method here, you should keep in mind that the functional used in DFT to represent the approximated exchange correlation functional is obtained based on the electron gas, on the solution of electron gas, and the solution of electron gas has been provided by Quantum Monte Carlo techniques. So whenever you run an DFT, there is a Quantum Monte Carlo behind it. That's the way I see DFT. And this also tells you that Quantum Monte Carlo is indeed a very important family of methods, which already made the history, if you like, of computational condensed matter physics, but then can be extended not only to the Gellium problem, which is a simplified, if you like, Hamiltonian, but also to more complex Hamiltonians, where you have the complexity of the structure, the chemical composition, and also the variety, if you like, of interactions which characterize the matter in all these forms. So the idea is to apply Quantum Monte Carlo to not only to simple, although very important Hamiltonians, but to a general ab initio Hamiltonian. Okay, so now when the choice of these three families becomes critical, so Quantum Monte Carlo, as I told you, is the theory of choice for a large system. Large systems, if you like to keep the high accuracy of the solution. And in particular, it's a method of choice in the presence of strong electron correlation. So what's meant by strong electron correlation? So you have a different definition of correlation structure depending on the community you're talking to. So you have systems which are strongly correlated because they are characterized by a strong local Coulomb repulsion. As I showed you before, you have if you like, the interaction between electrons in some particular configurations becomes relevant. Becomes the most relevant interaction in the Hamiltonian. And we're going to see later some examples of systems where the Coulomb repulsion is very strong. Another case where we can talk about strong correlation is, if you like, the dissociation limit of a molecule. Okay, you take, for instance, a diatomic molecule, you pull apart the atoms constituting this molecule, and when the atoms are far enough apart, you are in the so-called dissociation limit. And that's a limit where the two atoms still feel an interaction, but this interaction is very subtle. And that's the way where strong correlation also plays a crucial role. So if you like, the dissociation limit of a molecule or a molecular complex is the strong correlation for a quantum chemist, for instance. In general, strongly correlated systems are systems where there is a predominance of charge and spin fluctuations, like for instance in Mott phases and magnetic phases of condensed matter. In these systems where the fluctuations are very strong, you need advanced methods like Quantum Monte Carlo. And in general, again, I'm just recalling this another time, stressing the importance of high accuracy when it is required. When you have competing phases, for instance, you'd like to compute a phase diagram of, for instance, water or hydrogen or another system, and you have many phases very near, very close in energy. And to resolve these energy differences, you have to, of course, to be as accurate, at least, as the energy differences, which are the target of your calculation. And this situation of a competing phases is quite common. So I would say, so it's a very important point. The phase diagram of materials is a charging problem in general, and where high accuracy is required. Another situation where high accuracy is required, for instance, in the case of layered materials, in which the interaction between layers is characterized by weak dispersive forces, like, for instance, graphite made of graphene sheets, or, you know, I mean, all layered materials we know, and also the most fancy one, like the twisted bilayer, for instance. The twisting the two layers is also stabilized by van der Waals interactions. And all these cases where you have weak dispersive forces are cases where Quantum Monte Carlo can make the difference. And then, in general, where you have a subtle interplay between structural and electronic degrees of freedom, that's also a situation where high accuracy is required, and Quantum Monte Carlo can be the choice. So I talked about Mott phases. So what we mean by Mott phases and Mott insulators and Mott physics in general. So so I talked about the localized Coulomb interaction. So we have seen in the Hamiltonian that the Coulomb interaction is generally written as the 1 over the distance between two electrons with a coupling E square, which is 1 in artery units. So that's the interaction. But in the case of strongly correlated systems, the peculiarity is that these electrons interacting through the 1 over r potential are localized, and are localized basically by the physics itself of the system. So they are sitting in orbitals which are localized, which are compact and centered around the nuclei. These orbitals, which are localized around nuclei, the most localized orbitals are the d or f orbitals, and so that's where strong electron correlation arises, usually in d or f materials. And if you compute now the average of the Coulomb interaction for these electrons living in the localized orbitals, you get this U term, the so-called U term. And I think you have heard about the Hubbard U interaction, which is basically given by this, if you like, projection of the Coulomb interaction with electrons living on low energy states, localized like in the D or F states. So in the case of large U, imagine that usually this U is very large for electrons sitting on the same site, the same nucleus. In the case of large local U, the electrons will try to avoid each other. So what you have is the double occupancies, so will be suppressed, and it's like the physics you can if you like visualize with this egg paper where you put balls on it and you shake it. At some point you're gonna get the balls sitting on the minima of this surface without possibly double occupancies, and the strong repulsion, local repulsion, will impede the particles to jump to the neighbors, because the neighbors will be occupied, and the particles will avoid each other. So you get into a frozen situation where each ball is seated on its side, and that's basically, if you like, the cartoon picture of a Mott transition where the charge is localized on each side due to the strong local repulsion between the electrons, which are represented by these red balls. Okay, that's one of the cases where DFT fails. Okay, so this was one of the questions I got in the chat. So DFT fails in these situations where you have strong correlation between D or F electrons. And if you like, the hand-waving argument to explain why DFT fails in this situation is that, again, DFT is based, the approximated function is based on the solution of the electron gas problem, which is the opposite limit, right? So the electron gas, the electrons are spread homogeneously in the space, while in this situation, the electrons are strongly localized. So that's, you can also, of course, have a deeper insight in this problem, but that's the hand-waving argument to explain why DFT fails in this limit, because it's very far from the limit used to build the approximated functions. Okay, so let's go ahead. Yeah, so just to show you other examples of systems where you have strong correlation, and what is the main effect of this strong correlation we're talking about. So it's seen in the band structure. So this is the band structure of a material. So it's the eigen energies as a function of the K point, okay, the momentum. And so if you compute the DFT bandwidth with yeah, so the band, if you compute the band structure with DFT, you get a bandwidth which is given, for instance, by this red arrow. But if you do the experiment, then you will realize that for this class of materials, which are called strongly correlated, usually the experimental bandwidth obtained, for instance, by ARPES, by angle resolved emission spectroscopy, is much smaller, is significantly smaller than the bandwidth computed by DFT. And so this reduced bandwidth is one of the manifestations of strong correlation in some physical properties. okay? And these physical properties in this situation are probed by ARPES, for instance, spectroscopy. So you have a band normalization which affects not only the band structure, but all the low energy properties like conductivity, if you like, absorption, and so on and so forth. So you have the a full set of properties which are strongly affected by the band structure of the material, and if you don't get the band structure right, you basically you spoil the predicted properties compared to the experimental ones. And that's, for instance, the case of this barium iron 2 arsenic 2, which is an unconventional superconductor, iron-based. Again, iron is a D element, so it's an element where the electrons are present, so they are localized, strongly localized, and where strong correlation is important. And that's the class of superconductors Sandro mentioned at the beginning as one of the targets and the challenges to explain superconductivity, which is one of the open issues in condensed matter physics, and maybe can be solved by in the near future by Quantum Monte Carlo. And so, of course, the band structure also determines what's called Fermi surface topology. So the Fermi surface will depend on the way the bands are arranged and they develop in the K-space, and the Fermi surface topology is again very important to determine, for instance, conductivity properties of the material. And so it's one of the quantities we'd like, or one of the features we'd like to compute accurately. And DFT usually gives contradictory answers if you use DFT in this material. So you get different answers according to different functionals. So the approximation, the DFT approximation, is very sensitive and will affect the actual outcome of the calculation. Okay, so another situation where correlation is important. Again, I was talking about dissociation limit for molecules. In this case, we are not really talking about dissociation limit, but already, if you like, how the energetics of the molecules evolve, for instance, as a function of the distance between fragments, is also sensitive to electron correlation. So I'm showing here two cases. So the Zundel ion on the left-hand side, and the protonated water hexamer on the right-hand side. So the Zundel ion is made of two water molecules, and in the middle there is a proton, H+. And that's a very important system to, if you like, it's a very small system. So it's also a benchmark system because you have accurate solutions by many methods. And that's basically a benchmark system. It's the first brick, the first building block to study the proton hopping. The proton hopping is a very important process occurring in water, but also ecosystems, and also in all systems where you put a water environment around. And so it's a key process to also understand protein folding and, in general, the water solvation of many biological molecules as well. So, so understanding proton transfer, proton hopping requires a very accurate determination of what is called the potential energy surface, or PES. And so here I'm just representing the PES along some, so the PES is a function, is a potential depending on many variables, all three n variables, where n is the number of ions in the system. And so here I'm just representing the PS projected on two coordinates, the distance between the two water molecules and and the distance between H plus and one of the two molecules, two oxygens. So, that's the minimum of the PS. Okay, I'm projecting on these two on the two coordinates, and you can see that the minimum of PS has basically at some point at two branches. So the proton is at some point when the two water molecules are far enough. The minimum is basically a double well potential. And this double wave potential basically is key to understand the proton hopping, because the proton hopping goes basically likes to tunnel, if you like, to go through this barrier in the middle. The location of this barrier is very sensitive to the method you use. So, for instance, in green, I report a PBE DFT solution of the problem. So you have a minimum which basically separates the location of 2.45 angstrom between two oxygens. If you do DFT with van der Waals correction, you get the purple curve with the separation which is a little bit shorter in distance between the two water molecules. And if you do QMC, which is our, of course, reference theory in this case. Also, you have in this case also other quantum chemistry methods working quite well, like MP2. If you do QMC or MP2, you get a separation of these two branches happening at much shorter distance between the two water molecules. So to show you that the correlation is not only, if you like, present in strong correlated materials, but electron correlation is also fundamental to get a very accurate potential energy surfaces. And in particular, if you look at some phenomena like proton hopping, getting an accurate potential energy surface will determine the right dynamics of the proton in the middle to jump between the two molecules. And the same situation happens if you hydrate the Zundel core by 4 more water molecules, and you get, even in this case, a strong dependence on the theory. So again, the choice of the theory is critical to get the right solution of your Hamiltonian, and so the right physical properties of your system. So again, I'm recalling you another time that we'd like to solve the Schrödinger equation, the eigenvalue equation involving the Hamiltonian H. And in general, we are interested in the full spectrum of the Hamiltonian, so all eigenstates. But so we're going to focus for a time being as a first, if you like, target to the ground state of this Hamiltonian. The ground state already tells you a lot of properties, although excited states are important as well. So for both the ground state and excited states, you can introduce the wave function written with some ansatz. Ansatz, it's a technical jargon to say I make some hypothesis about the form of the wave function, and that's basically the form used in the Quantum Monte Carlo theories we're going to talk about during this week. So that's basically an explicitly correlated form, okay, which is made of a product of the Jastrow factor. Sandro mentioned this morning. So you're gonna hear about Jastrow factor many times, and this, which is highlighted here in light blue, times the antisymmetric part for electrons, which can be a single Slater determinant or a linear combination of Slater determinants. So that's basically a general form for the Quantum Monte Carlo wave function, okay? And you can see here that while post-Hartree-Fock methods are basically written in the yellow form, so they are all based on a linear expansion of the wave function in determinants. The D are the determinants. If you like, the Quantum Monte Carlo novelty, or if you like, the step forward in the way the wave function is written is to condense electron correlation in a clever way in the Jastrow factor. Okay, so there is an explicit correlation because the Jastrow factor, Sandro is going to explain it tomorrow, is a pairwise. Usually, it's written in pairwise form, so it's an explicitly correlating form. This is basically, it's a way to compact, to write in a compact way electron correlation in a given ansatz. Okay. So, and the correlation described by the Jastrow factor is usually called dynamical correlation because it involves the position of pairwise electrons. And the correlation, which is still present and it can be included in Quantum Monte Carlo as well, which is obtained by a linear development in Slater determinants, is called usually static correlation. So in Quantum Monte Carlo, you have the presence in these ansatz of both dynamical correlation through the Jastrow factor and static correlation through an explicit expansion in Slater determinants. So we ended up with a nice, clever way of representing correlation. Again, this part will be treated by Sandro starting from tomorrow, so I won't enter in the details here. So we have a compact way of writing the wave function, but there is a drawback. Okay, the drawback is that so when I'd like to compute the expectation value of the Hamiltonian over the wave function, which is this E here, psi h psi over the normalization, I have to compute both overlap integrals of type psi psi and also Hamiltonian integrals of type psi h psi. So these integrals are multi-dimensional because psi again is depends on n electrons, so 3n coordinates. And in the case of a clever, explicitly correlated wave function, like the one used in Quantum Monte Carlo, these integrals are much harder to compute than in the case of a simpler trifoc. In simpler trifoc, you would have, if you like, just a form which involves one body integrals. Here, you have to keep a many body integration because you're dealing with a correlated wave function. So, so we gain in, if you like, by writing down a nice form, including correlation in an explicit way, but you lose in the sense you have to change, you have to evaluate this many body integration, multidimensional integration in a way which is not the one used in trifoc. So you should use a way which is efficient enough to make the calculation doable even with this explicitly correlated wave function. And so, you can always, then this basically boils down to an integration problem, okay? And so again, so we have to compute these kind of integrals, and then you should look if you like, in the tools which have been developed and choose the proper tool. So which tools have been developed to solve multidimensional integrals? So one tool, so one family of methods, integration methods, belongs to deterministic integrations a la Simpson, okay? And we're gonna see that those are feasible for our purposes. And then there is another, if you like, a family of tools, of mathematical tools, to compute these integrals, which are the stochastic integration. And so in the case of multidimensional integrals, the stochastic integration will be, without any doubts, the method to use, okay? And so stochasticity, if you like, enters in the task of computing a multidimensional integral of this type here, psi h psi over psi psi. Okay, So now we're gonna see why a deterministic approach to the integration is not doable, and why instead the stochastic integration is the way to go. Okay, let's start with the deterministic integration. Okay, so what I'm doing with the deterministic integration, maybe I can try to use my tablet here. Let me see if I can switch these.
Michele,
Yes.
there are a couple of questions in the chat.
Yes.
I'm not sure if you want to keep them.
Okay, let me, because I don't have a double screen, unfortunately. I just have my laptop screen. I just put the chat on the bottom bar. So let me see if I can open the chat now. Yes, the chat is here. Okay, let me see. Huh? Let me see. Go back here. Okay, the chat participants. Okay.
Well, I can read them loud if you like. You should have a button probably in your Zoom.
Yes, I should have button. You're right.
So there is one from BB. What are the failures of DFT?
Yes, so yeah, I've explained the failures before with these examples. So, you know, strongly correlated systems. So basically, those systems are systems involving D or and F electrons, and the failures also are present where we'd like to compute potential energy surfaces of molecules. Or molecular complexes where we'd like to study the energetics of the molecular dissociation or the molecular dynamics. So I provided basically two examples, one based on condensed matter systems and the other based on quantum chemistry systems. So those are, yeah, for me are the two, the most if you like, those are textbook examples for failures, for DFT failures, but they're also important to illustrate also the importance of using Quantum Monte Carlo in these situations. So I think I addressed this question in the slides. Sara, what is the next question?
Yeah, even in the conjugated systems with the p electrons, DFT fails. What is the cause? Probably linked to
yes. So in that case, the cause is related to another situation, which is the spectrum of the conjugated systems, pi star systems, is characterized by many low-lying energy states, which are nearly degenerate. Okay, so in the case of near degeneracy of states, you have a strong correlation as well, because these states are competing each other, being nearly degenerate, and to resolve the competition between these states, you need to use many-body methods like Quantum Monte Carlo, and DFT will choose one of these states by neglecting, if you like, the presence of the others. So because DFT is built on a density which is constructed, the density is constructed using a reference system which is non-interacting, and so it fills the first n states and disregards the states above. Now, if the states above are very close in energy, you'll miss important correlations between the first n states and those which are above, but important to be taken because close in energy. So that's another, yeah, it's a good point. So it's another class of systems where strong correlation is important. It's due to nearly degenerate states in energy. Yeah, so what is the next? Sorry, Sara, I'm still not able to, I don't know why, because usually it's a stupid solution of getting the chat, but
don't worry. And there is another one. So yes. USB has highly localized bands in DFT calculations. I should expect errors in the values calculated, I assume. Is it possible to calculate this system using Quantum Monte Carlo method? Can we work this on a basic computer?
Yeah, so I mean, if I understood correctly, the question is about this flat band behavior, right? Yeah, so I think with the development of HPC systems, HPC architectures, with the increasing of computing power, as Sandro mentioned at the introduction, the exascale business, with all these hardware, if you like, tools, and with the development of the softwares like Quantum Monte Carlo, TurboRVB, the solution of complex ab initio problems involving many electrons and many ions would be, if you like, more and more doable in the future, in the near future. So we have already, if you like, published results on the coup rates, for instance, where you have a stronger normalization of the band structure. But there are a few papers so far published, but I think the future in this sense is bright, because both hardware developments and software developments are converging to allow tackling these problems using Quantum Monte Carlo in the near future. Yeah, so I'm optimistic from this viewpoint.
And one last question. So Shivam is asking, there is a method to calculate the strong correlations by the DMFT and random phase approximation with linear response method. How is this different than this way?
Okay, so that's a very good question. Indeed, Quantum Monte Carlo is not the only many-body method used to study strongly correlated systems. And you know, there is another family of methods mentioned by the student or the person who asked this question. So that's basically dynamical mean field theory, DMFT. So what is the difference in a nutshell between Quantum Monte Carlo and DMFT? By the way, Quantum Monte Carlo, in a most general sense, not the Quantum Monte Carlo we are presenting this week, so which is called continuum Quantum Monte Carlo, where, if you like, we deal with electrons moving in the phase space, in the Cartesian phase space. Quantum Monte Carlo in general is used in different situations, okay, and is used also to compute many-body green functions, so Quantum Monte Carlo is used. Not the one of this week's lectures, but in the Quantum Monte Carlo, called continuous line Quantum Monte Carlo, is used to solve the many-body problem built in the dynamical mean field theory. So, okay, so instead of clarifying the situation, I make it more complex, I realize. So what is, so before we should distinguish between DMFT and Quantum Monte Carlo. What is the difference? DMFT is a method where the many-body part, if you like, is atomic-like, okay? So DMFT is a method which is based on the embedding of an atomic problem into a medium which is represented by the crystal, okay? While our Quantum Monte Carlo treats, if you like, correlations at all levels, not only at atomic level, but also at nearest neighbor, next nearest neighbor level. So it's built on a full many-body expansion, while the dynamical mean field theory is built on the expansion of the atomic problem. Okay. So that's the main difference, which of course, tells you that Quantum Monte Carlo, wave function Quantum Monte Carlo, is the method to go in the case the correlation is not atomic-like, it's beyond atomic, which is the general case, by the way. So the atomic embedding is a very strong approximation in dynamic field theory. So it's a very strong approximation which holds only in particular cases where the leading order of the interaction is atomic. So basically it's restricted to D systems, F systems, but is for molecules, so forget it. Okay. On the other hand, the dynamic field theory has the possibility to access the full spectrum of the problem, because the atomic solution is solved basically at not only for the ground state but also for the excited state. So you have a green function representation of your problem. So you have the access to all processes involving the diffusion, the scattering of an electron going through the medium, and basically exciting basically the medium, fully exciting the medium. So you have a green function, if you like, approach to the problem. I'd like to stress again that the Quantum Monte Carlo is present also in dynamic field theory, because the solution of the atomic problem is based on Quantum Monte Carlo algorithms, which are not the one, again, of this week, but there are particular algorithms which are still stochastic in their nature. Okay? So and this is one of the solvers, called solvers. I think I have addressed this question. What is the next, Sara? No,
I think that's it for
okay,
the moment.
Good. So
yeah.
Okay, so it's 10:30. Let me finish at this part, because it's very important. Otherwise, we're gonna run out of time at the end. So I'd like to finish. I mean, some content should be addressed today, otherwise Sandro tomorrow will not be able to start his lectures. Okay, so let me finish about the multidimensional integration, and then so I'll stop for the break. We were discussing about the difference between multidimensional integration, difference between deterministic and stochastic methods. If you like, if you take a deterministic method, so you'd like to basically divide your domain, integration domain, into a mesh. Okay, so deterministic integration, you compute the integrand over a mesh. Okay, and let's say, for instance, you have an integration over a space made of n electrons in d dimensions, and for each axis you have 10 mesh points, for instance. Okay, so you take 10 mesh points for each axis, and so how many points you have? You have 10 to d times n. Okay, so you have the full grid is made of 10 to the d times n, because you have d times n axis. For each Cartesian component of each particle, you have an axis, and the axis is divided into 10 mesh points to compute the integrand and to sum the integrands over the mesh. So you have basically, and you have to compute the integrand at each mesh point. So you have 10 to 30 operations, okay, for 10 particles in 3 dimensions. So imagine that the calculation of the integrand on each of these points takes, let's say, 10 to -9 seconds. Okay, let's say you have a computer fast enough to compute to evaluate the integrand in 10 to -9 seconds. Now, what is the total time? So you have to multiply to compute the integral. You have to multiply each point, which takes 10 to -9 seconds, times 10 to 30. Okay, If you do that, you realize that this integration will take too much time. In particular, it will take 3 times 10 to 13 years. Okay, if you think that the age of the universe is about 10 to 9 years, you realize that this is virtually impossible to compute, even for this, Gedanken. This Gedanken, if you like, Gedanken approach will tell you that a deterministic quadrature scheme is nominally impossible for 10 particles in 3 dimensions, even if you accept to compute only 10 mesh points per axis, which is anyway a few points for a complex integral. So it's clearly doomed to failure. But what could be the approach? The approach is, okay, I accept to make an error, okay, and so which is my target error. And by the way, this approach is the way of thinking you should have in all the problems you'd like to solve. So you should keep in mind that you'd like to solve a given problem with the target error, which is small enough to resolve the properties you'd like to get. Okay, so let's keep this good mindset. So we'd like to compute the integral in a reasonable amount of time at a fixed target error, and the question is how this error scales with the number of points of the integration scheme. So the number of points m. So again, I'm taking again the quadrature approach. So now I'm doing more general, more formal. I have an hypercube of side L, okay, and the mesh size is H. The number of grid points is M equal to L over H to D times N. And so the mesh size H depends on M in this way. So it's M to -1 over D times N. And so in the quadrature, in the Simpson approach, depending on the Simpson rules, the error scales as a power law of H. Okay, let's say H to the L power. Okay, and so what is the error now of my Simpson integration? Is 1 over M to L over D times N. And so this error decays exceedingly slow with M. And in fact, the larger N, the slower is the decay. Okay, and so if you'd like to basically understand how this scales with the number of points M, you realize that the scaling is exponentially increasing with the accuracy you'd like to get. So for instance, for halving the error in the case of 10 particles in 3 dimensions with the Simpson's rule giving L equal to 4, this the error scaling. You can do the algebra. You get to halving the error. You get to increase the number of mesh points by 180, and to reduce the error by a factor of 4. This requires 10 to 5 times m points with respect to the reference calculation. So you have to increase the number. So if you'd like to decrease the error, you have to increase the number of integration points m in an exponential way. Yeah, so that's basically the situation. And now, what is the situation now for the Monte Carlo integration? The Monte Carlo integration, you have a completely different behavior. Okay, so let's say this is the integral you'd like to compute. Okay, so again, R is the the n-dimensional vector of your integration. So that's, if you like, the integrand. So the integrand is split here into parts, a pi part, a pi factor, and O factor. The pi factor should be positive definite, okay? And O can be also negative, if you like. So if you are able to split the integrand in this way by a product of pi and O, if pi is positive definite, you can normalize it. So you can interpret this as a probability distribution. And so this can be now rewritten in terms of a sum of, it's a sum over m points. Again, this m is the size of your points. The integrand is resolved, and this, in the stochastic approach of the n-dimensional integration, these Ri points are distributed according to pi of r. Okay, and so you compute the integral as a sum over Ri points, as a sum of O, the second factor of the integrand, computed at Ri points, and these Ri points are distributed according to pi of r. If you rewrite the integrand in this way, and you compute the integral in this way, the error you make in the evaluation of the integrand, scales as 1 over square root of n. Okay, and that's due to the central limit theorem we're going to see later. And so this is this scaling is completely different with respect to the scaling of the Simpson approach. Okay, again, if you take the same spirit of halving the error or getting an error reduced by a factor of 4, if you'd like to halve the error due to this scaling, the error scaling with m, you just to increase the number of points by a factor of 4. If you'd like to get the error 1/4 of the previous error, you should increase the number of points by a factor of 16. That's very different from the factor 10 to the 5 we have seen before. So that's basically to summarize what we have seen. So in the deterministic integration, if you'd like to reduce the error by a factor of k, the number of mesh points and prime scale in this way, okay, in the exponential behavior with the number of particles, while in the stochastic integration, the mesh points and prime scales in this way, k squared times n, which is independent of n. So so the scaling of the mesh points to reduce the error by a factor of k is independent of n, is no longer exponentially large. Okay, so it's clear that for large enough systems, the stochastic integration will win, and the deterministic integration should be abandoned. Okay, so I stop here, and then we resume. So what is the schedule, Sara, for the next lecture? We're going to start at 11.
Yeah, it was I think 10:50, but we can. I think we can take.
Okay, I think we can take it.
If it's fun for you to start at 11, so we have 2 other. No, one lecture. Sorry, after yours again after 12:30. Then until 12:30. So.
Yeah, so I think we can resume at 11. I think it's we can have a 15 minutes break. Yes.
Yeah. Mm-hmm. So just leave the Zoom as it is. Simply, I mean, stay muted and leave the camera off if you like. So you don't need to go out.
Okay. Okay. Good. Mm-hmm.
There is Bibi asking if you can show the previous slide.
Okay. Let me see.
And maybe Michele.
No. What is it?
not sure, but what I would suggest, yes, she says he or she apologizes, says yes. And what I would suggest, if you can share the updated slides, Michele, with us in the break, we'll make them available online.
Yes, sure. Okay, so this was the previous slide you were referring to.
Yes.
Okay. Good. Okay. All right. So
okay. So
I'll upload the slides so it will be available for everybody. Yes, over the break. Okay. So we'll resume in 15 minutes or so at 11 o'clock. Okay. Yeah. See you later. Thanks.
Hi all, welcome back. Let's see if Michele is also back.
Yes, I am back. All right, so let's start again. I'll share my screen again.
Yeah, for me it's okay.
Okay, so can you see it again?
Yes.
Okay, good. All right, so let's go ahead because we have many things to talk about before the end of this morning session. All right, so let's now move to the question. So just to recall you, we established that the stochastic integration is the way to go. So you split the integrand in the product of positive definite function pi, you interpret as probability distribution, and the other product, the other factor O. So now you need to, in order to compute the integral in a stochastic way, you need to generate the points Ri distributed according to the probability pi of R. And so the question is now how to generate this configuration Ri distributed according to pi of Ri. And so the answer, the easiest answer to this question is by using random numbers. So what does it mean? So what a random number is? A random number is a sequence. Random numbers belong to a sequence of random numbers drawn from an assigned probability density. Let's say u of x, okay? And so u of x times dx is the probability that x falls between x and x plus dx. An important, so two important properties of any probability density are the fact that u of x is, again, I repeat again, so should be positive definite, and the second property is that it should be normalized. And so that's the normalization condition here in blue. So you have different possible probability densities you can imagine of, and I'd like to separate them into two categories. One is the uniform variates, like, for instance, the u of x being 1 defined between 0 and 1, so the homogeneous distribution between 0 and 1. And if you'd like to extend this on a larger range, x range, for instance, from alpha to beta, u of x will have this value here, homogeneous flat from alpha to beta with a height of 1 over beta minus alpha for normalization. Other variates can be the exponential one, e2 minus y, or the normal one, which is very important in probability theory, whose range goes from minus infinity to plus infinity. All right, so so how can we play with random numbers using our computers? So, so let's concentrate ourselves on the uniform distribution, so the flat one between 0 and 1. So we'd like to have a generator, a random number generator, okay? And so what will be the features of this random number generator? This will produce values of x placed randomly in the interval 0, 1. And for large generation numbers, let's say you generated many times x values, those will be uniformly distributed, of course, between 0 and 1, because our target distribution is a uniform variate. And for large generation numbers, both average and variance of the generated X values will reproduce the average and variance of the assigned uniform distribution. Okay, so the generator will be compliant with respect a given uniform variate if the random numbers generated by the generator will be distributed accordingly. So again, it means that both average and variance of these generated values will perfectly reproduce the average and variance of the assigned distribution. So this sequence of random numbers can be generated on the computers, but in practice, these sequences are generated by deterministic rules. Okay, it means that these sequences are perfectly reproducible. So if you start from the first value, the same first value, this same first value will be followed by the same sequence. So we don't want to enter into the details of how this sequence is generated. So that's basically, it's behind the random number generator. But keep in mind that on the computer, we are able to generate random numbers through a deterministic sequence, but this sequence will look like a completely random, in the sense that the sequence will generate numbers whose average and variance will be the average and variance of the uniform distribution, and in particular for the one which is uniform from 0 and 1. Okay, so the pseudo-random number generator will generate random numbers uniformly distributed from 0 and 1. And now the question is how we can generate random numbers distributed according to a non-uniform variates, starting from our pseudo-random number generator, which generates uniform random numbers from 0 and 1. Because in general, our pi of x, the probability density distribution we'd like to compute in order to evaluate our integrand, our integral, this pi of x will be non-uniform. So we need to exploit our generator built by algorithms in our computer to produce at the end non-uniform variates. So there are different methods to sample non-uniform variates. The first one is the inversion method. Okay, so let's take pi of y as our non-uniform variate, and we'd like to generate numbers y distributed according to pi of y from random numbers x distributed uniformly from 0 to 1. So to make these y numbers distributed according to pi of y, we'd like to find the function f, which maps the x random numbers uniformly distributed from 0 to 1 to the y random numbers. And so this f function is our target. So we'd like to find it. Okay. So we start from this equation, which is basically, it's nothing else than norm conservation. So u of x times dx is equal to pi of y times dy. And so we can integrate now this relation, both right hand and left hand sides. And we know that y of x is equal to 1, from 0 to 1. So we replace y of x with 1, and by integrating this, we get this, this relation. So we get x equal to the indefinite integral of y, where now the integrand is pi of y prime. Okay, so so now imagine that we are able to integrate pi of y prime, and we imagine that we are able to find analytically this indefinite integral of y. And so we get this function w of y. If we invert this function w, okay, we get by inverting this function w, we get the actual function f we are looking for. Okay, so now the function f is the inverse of w evaluated at x. So in this way, we found how to generate random numbers y distributed according to pi once we have random numbers x distributed from homogeneously, uniformly from 0 to 1. The problem, of course, is to evaluate this integrand, if you like, this pi, the integral of pi of y, and in general, this is not known. Analytically, this is not known. So the inversion method is not a way to go for a general probability pi. So another way of sampling non-uniform variates is the rejection method. In the rejection method, so you make basically you build up a scheme where f of y, so where pi of y is now a function which is defined on a compact domain. So in order to build this rejection method, yes, so you need to have basically a compact domain for pi of y, and this pi of y will map the domain into an interval from 0 to a maximum value pi max. Okay, so maybe it's better to represent it graphically on. Let's see if I be able to use my tablet. Okay. So that's the rejection method. Okay. So you have function pi of y, distribution. Okay, that's a pi of y. And you'd like your y points, random numbers, distributed according to pi of y. So here you see you have a compact domain. So you have y min and y max. And you have also a compact codomain, so the function will map the y max y min interval into values flattening up, reaching the maximum value pi max. Okay, so in practice we're going to use this box here for the rejection method. So you define a box where the x range is going from y min and y max, and the y range is going from 0 to pi max. Okay. And now you what you do, you follow the following scheme. So you draw a random number, let's say chi, distributed from homogeneously from y min and y max. So chi, it's homogeneously distributed. And so imagine that you draw a random number from which follows, for instance, here. Okay? And once you get this chi number, then you generate another random number. Let's call it phi, which is distributed homogeneously from 0 to pi max. Okay? And now these can follow either below, let's say here, below pi of chi, or above. Now can follow here or there. Okay. Now if phi is less than pi of chi, you accept the generation of phi. Otherwise, you reject. Okay? And so in this way, you're able to generate, you can show that the phi will be distributed according to pi to pi. Okay. Of course, this we go through a rejection procedure, which is this one. So you're gonna draw another two random numbers. Okay. First, this one, chi. And then when you draw chi, you generate this phi, and you compare phi with pi of chi. So there is a comparison here and a rejection. Okay, so this rejection, so the advantage of this method is that you're going to sample a very general pi of y, because this pi of y is a very general function. Okay. On the other hand, you reject some some proposals. And this rejection makes the method quite inefficient. So you'd like to improve it. Okay. So basically that's the description here in these steps. So I mean, a note about this rejection method is that the normalization of pi is not necessary, okay? So you just need to know the maximum value of pi, and you need just to compare random numbers each other. So the Metropolis method is a particular rejection method, but Metropolis method is much more efficient. And we're going to see why. Why this, if you like, this rejection method is not efficient in the way I presented it, because imagine that pi has a region of low and high probability. In the region of low probabilities, you're going to reject many proposed values. And so you're going to lose time, okay? So we'd like to find a way where all the proposed values are acceptable and acceptable values in the sense that values distributed according to the target distribution. And so we'd like to invent an alternative manner to generate a sequence of states, the sequence called, like in this case, S1, S2, Sm, with all these sequence, those are all values which are acceptable in the sense that all those values are distributed according to the chosen pi of S. And the way to generate a chain sequence of states, all of them distributed according to pi of S, according to pi, without rejecting, if you like, them, so all of them are valuable. A way of generating this sequence is built on the concept of a Markov chain. Okay, so what is a Markov chain? A Markov chain is a sequence S1, S2, Sm, for instance, where the n element depends only on the value of the n-1 step. Okay, so it's, if you like, the memory of this chain is made just by the previous element. And the next element, S of n, is drawn based on the value of the previous one, according to a probability matrix, or probability general function. I'm going to call it matrix because it depends on two values, on two entries, which is given by P here, okay? All right? So, again, so the Markov chain is fully specified by the initial distribution, pi naught of S, and by the transition probability P of Sn prime. And so all this chain provides a convenient way to sample multidimensional probability distributions in a very general way. So imagine that you now you are at position configuration S, and you like to draw a new position, new configuration, S prime, and that's basically done through the transition probability P Sn prime. So this probability P Sn prime should satisfy the following properties. So it's a normalization property. So the sum over the possible outcome of the transition, all the possible S prime connected to the state S is 1. And of course, each event connecting S with S prime should have a positive definite probability. So these again are two conditions, the positive definiteness and the normalization, as usual in probability theory. So now we have defined the Markov chain. The sequence is generated through this transition probability P. All elements, each element depends just on the previous one in the chain. Fine, so far so good. But how can we assure that this sequence, S1, S2, Sm, is distributed according to our target probability measure pi? That's basically the same question, how to make this chain distributed according to pi. To answer this question, we should basically exploit, which is called the stationarity condition, here in red, which is the following equation, okay? So the stationarity condition tells you that the flux of the processes going from S to S prime, the sum of all possible processes going from S to S prime, contributes to a probability distribution which is pi of S prime. So you see here that this P basically connects pi, which is the target probability, on both sides of the equation, and this is the condition which tells you that in the case you generate a Markov chain according to P, the sampled distribution by the random chain, the Markov chain, is the probability pi. So how can we exploit further this relation, this stationary condition? We can exploit it further by relying on the condition which is called detailed balance condition. So, which is a sufficient condition to obtain pi as stationary distribution. So what is the detailed balance condition? The detailed balance tells you that pi s times p s prime is equal to pi s prime times p s prime s. So maybe I can use again my tablet to illustrate this more clearly. Okay, so now we have seen now the stationary condition, right? I'm going to repeat it. Okay, so we was telling that you have the S prime state here, and you have the collection of S states around. All are S states, okay? And the points indicate a state or a configuration of the system. And so the stationary condition, so the sum over S of of pi s times p s s prime was equal to pi, is equal to pi s prime. So if you like, so this can be pictorially represented by the sum of all fluxes of the system going to S prime. So let's change the color here. So in red, so the flux of the moves pointing to S prime, summing all of them, will add up to this value pi of S prime. Okay, and the flux for me, this red line, is the product of pi times p, the flux from S to S prime. Now, in the case of the detailed balance condition, instead of a global property where you have to sum over all S states, I have a local property connecting just one S prime and one S states. And so again, so the detailed balance is such that pi of S times P S S prime is equal to pi of S prime times P of S prime S. Okay? So, and I can represent this by two arrows. So the flux going from S prime to S, and the backwards arrow, the flux going from S to S prime. Okay? This is the backwards arrow in blue, and in the green it was the forward arrow here. Okay. So how can we be sure that this detailed balance condition is a sufficient condition to get the stationary equation making the Markov chain converging to the probability pi? So we can show this. We can show that the detailed balance will imply the stationary condition. Okay, so let's show this. Okay, I'll just erase this. Okay, so let's start from the detailed balance again. So, whoop. So pi of S P S S prime equal to pi of S prime P S prime S. So we sum now over S. Okay. And so because our goal is to find this relation here, right? If it's fulfilled or not. So we need to sum over S. And so, of course, both sides, right? Both left-hand side and right-hand side. So now look at the right-hand side. This pi of S prime doesn't depend on S, so this can be pulled out of the summation symbol. Okay, so you have pi of S prime sum over S of P S S prime. but then you know, P S prime S, but then you know that this one is equal to 1 because P is normalized. Okay, so that's one of the two conditions for a probability defined in the Markov chain. And so you end up with pi of S prime. Okay, and so at the end, you recover that the stationary condition, which is this one, equal to that one. Okay, so we have seen that the detailed balance condition is a sufficient condition to impose the validity of the stationary condition. And so if P is such that this relation is fulfilled, P will generate a random chain with a sequence sampling exactly pi of S. Okay, let's go to the slides again. Okay, so there are questions on the chat, maybe? I don't know. Okay. All right.
No, we don't see questions, but I take the chance to say that actually, if anybody needs to open the microphone and talk, maybe raise your hand, and we'll allow you to do so.
Mm-hmm. Okay, so let's go ahead. So now, now we have a recipe, if you like, to define a probability P such that the target, by probability P, it's a transition probability. So we are talking about different probabilities here. So P is the transition probability and pi is our final distribution. Okay, so we have a recipe to define a transition probability P in such a way that we're going to sample the final distribution pi by this Markov chain process. Now, we can refine further this transition probability P by splitting into factors. A factor capital T, which is called the proposal or sampling matrix or probability, TSS prime, and the other factor, which is the acceptance matrix A. Okay, so why we are splitting this into factors? This is we're going to mention this later, particularly in diffusion Monte Carlo techniques. This is to, if you like, improve the way the S prime is sampled. So it increases the efficiency of the chain, the sequence, the Markov chain sequence, to reduce some particular property which is called autocorrelation time. So, and to speed up, if you like, the sampling of the probability final probability pi. Okay, so it's a way to optimize the exploration of the configurations S, such that the chain S1, Sn will effectively sample pi. Given this definition, so again, so the sampling, this proposal of sampling matrix is something we'd like to sort of impose, so it's known. So what is left to determine is A of SS prime. Okay, so we have to solve the detailed balance condition now for A. And if you solve the detailed balance condition for A, you realize that we will end up with this relation. Okay, so the acceptance matrix A, or acceptance probability A, is such that this ratio ASS prime divided by AS prime S is equal to this ratio there. Okay, and so this ratio there depends on known quantities, in the sense that pi is our target, we know, we'd like to sample. and T is also known because we'd like to impose an efficient proposal or sampling probability to our evolution of the Markov chain. So we can define this ratio as Q, okay, Q SS prime, right? So we define this as Q SS prime. And so what is now A, such that this will fulfill this relation? So we can satisfy generally the previous relation by choosing A SS prime equal to F of Q SS prime, where now F is just a function of Q SS prime, but which form for this function? The function should go from is a function from a domain ranging from 0 to infinity to a space defined from values from 0 to 1, because A is a probability. So this function F is basically should have the property that F of Z divided by F of 1 over Z is equal to Z, okay? So if this function F fulfill this relation, then our A SS prime will fulfill the detailed balance condition written in this way, okay? So so that's basically the most general choice to define the acceptance probability A. And so you have different choices. So if you like, I can show this relation. So let me switch to the tablet. So we have seen that, so we have the acceptance probability. Okay, to be determined is such that A S prime divided by A S prime S is equal to pi S prime times T S prime S divided by pi of S times T S prime. Okay, and we have seen that this part is known because we know pi and we'd like to sample it, and we impose an efficient transition probability T. So this is known and it's defined as Q S prime. Okay, so we'd like to show that if I define A S prime as equal to a function capital F depending on Q S prime, in this case, if F is such that F of Z divided by F of 1 over Z is equal to Z, then if F is such that this relation is fulfilled, then 1 is fulfilled as well. 1 is fulfilled. Okay. So yeah. So how to show this? So first of all, you should realize that if you compute Q of S prime S, you should observe that Q S prime S is equal to 1 over Q S S prime. Okay? And this is very easy to show just by inspecting the definition of Q. Okay? So if you replace S with S prime and S prime with S, if you permute S S prime, you realize that Q S S prime is the inverse of Q. Q S prime S is the inverse of Q S S prime. And then you simply apply the definition of A of S S prime in terms of F. So now this so A S S prime divided by A of S prime S is equal to F of Q S S prime divided by F of Q S prime S, but this is nothing else than F of Q S S prime divided by F of 1 over Q S S prime, okay? Because of this relation here. This one, okay? Applied to the denominator. And so now, if we define Q S S prime as Z, you realize that this, so I'm replacing this in this way. So this should be F of Z divided by F of 1 over Z. And by definition of F, this will be equal to Z. But Z, again, is QSS prime. So you realize that we have found the relation we are looking for. So A SS prime over A S prime S is equal to Q SS prime. Okay? So now we have a form, a functional form, upon which we can define our acceptance probability in a way, in a very general way, such that the detailed balance condition is fulfilled. Okay. So now let's see what are the possibilities. So it's a very general form, right? So this can be specified with different functional capital F. In particular, there are two possible choices for this capital F. One is the metropolis choice. So capital F of Z is the minimum between 1 and Z. And another possible choice could be this F of Z equal to Z over 1 plus Z. That's another possibility which fulfill this general relation here. So, but metropolis choice is this one, okay? And so we stick with this definition for F of Z. And again, it's possible to show that if that this actual form fulfills this relation here, okay? So I think I can leave it for your homework to show that the minimum between 1 and Z we fulfill this general relation here, and so we fulfill the detailed balance condition for A. Okay, so now we can introduce a general implementation of the Metropolis algorithm. So we have all the ingredients to define the operational implementation of this algorithm. Okay, so again, the target is probability pi. We'd like to sample with pi of s, with s as state of the system, and we like to basically generate a chain, a Markov chain distributed according to pi of s. We choose a proposal matrix of probability T of SS prime. Usually, we choose a homogeneous distribution, although it's not always the case, from basically in the interval minus delta plus delta from the state S. Okay, so we propose a new move according to a homogeneous distribution centered around the previous configuration, the starting configuration S, within some interval which is given by this delta range. Let's say we initialize the system in the state S0, which is the first point in my chain, and we'd like to make the chain evolving, where now the steps are defined with the index n, and imagine that we'd like to move from n to n plus 1. Okay, so to move from n to n plus 1, I have to first to sample S prime, the attempted move from S of n, according to the proposal probability T. Okay, again, in the case of homogeneous move in a box, my S prime will be equal to the previous S of n plus 2r minus 1 times delta, where r is a random number distributed according to the uniform variate from 0 to 1. Okay, so this random number drawn will propose an S prime homogeneously distributed in a box of size 2 delta, centered around the position configuration S of n. Okay, so then I calculate the probability Q, right, according to the detailed balance condition. So now I'm applying the detailed balance condition to know whether this attempted move S prime should be accepted or not. All right? And so that's the Q probability, which depends on the ratio between pi computed at a new position, attempted new position S prime, divided by pi computed at the former position S n, modulated by the homogeneous, modulated by the proposal matrix T. Now, if the proposal matrix T is homogeneous, this will disappear in the ratio. Okay. Now, I should accept or reject according to acceptance probability A, and A is defined as a minimum between this Q and 1, as we've seen before. Okay, the acceptance probability is the minimum between Q and 1. And so now I draw another random number xi, distributed uniformly from 0 to 1, and I compare this random number xi with this probability f. Okay, so if this random number is smaller than f, then I accept the new the attempted move, and this move will become the new step in the chain, the n+1 step in the chain. Otherwise, if xi is larger than f, I reject this move, and the n+1 step of the chain will be equal to the former element S of n. Okay. So I draw your attention to this important point. So there is a acceptance rejection step here in the Metropolis algorithm, as we have seen in the rejection method, with the first very simple rejection method. What is the difference, the important difference here? The important difference here is that even if I reject, I generate a new element in the chain. So the rejection is not a waste, if you like, a total waste, because if I reject, I add anyway a new member in the chain, which is in this case equal to the former member. Okay, and so the fact that while rejecting, I still keep the member as a replica of the former member is an important feature of the Markov chain built in this way in the Metropolis algorithm. Okay, and so if you like, the multiplicity of equal terms in the chain is important. It means that that particular state, which appears more than one time, has significant relevance for sampling the target probability pi. Okay, so the rejection somehow is not a waste, as in the dumb method, the initial dumb method, but the rejection is always constructive in the sense that it in that case it just keeps going the evolution with the previous iteration, with the previous state. Okay, so so just some comments on the Metropolis algorithm. If again T is homogeneous, okay, as just mentioned to you before, in particular, I mean more generally, if T is symmetric, okay, then T disappears from this probability Q. So the acceptance probability depends only in that case on the ratio between the target distribution pi, okay? And so in that case, if the proposal matrix T is symmetric or in general is homogeneous, as in the box I mentioned before around the previous state, in the case of this situation, the algorithm is called simple Metropolis. Okay, in the case instead the proposal probability T is non-symmetric, and that's basically due, that can be conceived to improve the efficiency, the sampling efficiency. In that case, the algorithm is called generalized Metropolis algorithm. Yes, so some other comments about the Metropolis algorithms. So, so again, we have seen here, right? So we started from configuration as naught, and then we evolved S1, S2, S3 according to this rule here. In general, Sn to Sn plus 1, where n greater than greater equal to 0. So I mean, S naught will be the first step, and then we'll proceed. So the first steps in the first steps, the system has still to equilibrate to the final target probability pi. So the first iterations in the chain, the first elements in the chain won't be representative of the target probability pi. And this is a very important, if you like, point to keep in mind, that you should equilibrate your chain such that at some point the chain will really sample pi. At the beginning is just a transient evolution towards pi. And to compute our integral, we should disregard these first iterations because those are not sampled according to pi. Okay, so the fact that the chain will converge finally to sampling pi is due, of course, to the steady condition, but the steady condition is reached after, let's say, k steps. So I should disregard the first k states as being out of equilibrium. So how can I determine these first k states to be disregarded? I can compare local quantities like energy or pressure, for instance, or other quantities, and I have to analyze the evolution of these the averages of these physical quantities and see at which point the averages, or if you like, the integration values I compute will stop having a drift and will start oscillating around the true average value. So I have to check, if you like, the evolution of the random chain by computing physical quantities or the integration values, which is the final goal of my random chain. And these integration values should stop drifting and start fluctuating around the converged final solution. Then I should, so what is left, which is the interesting part, the interesting states, which will provide to me my final value for the integral. These next steps, which is the most important part of the random on the Markov chain, the next steps should be analyzed with methods I'm going to talk about in a few minutes, by computing both average and error. Okay, so because the stochastic method will have an intrinsic stochastic noise and the stochastic error bar. So it should compute both average and error based on the good steps in the Markov chain after these first k states. An important observation is that in all the derivation I propose to you, there is no need of normalization of pi of s. And that's a very important property, because you see pi enters in the algorithm only as a ratio, okay? And so I can completely simplify, I can fully simplify the normalization condition, which basically cancels out in the ratio. So that's a very important point, because the normalization of pi sometimes is very hard to compute, or is impossible to compute. So I know the local value of pi of s unnormalized, because pi can be a very good definition of probability distribution being pi positive definite, but the normalization sometimes is not computable, and here the advantage is that it is not necessary. So pi can be taken unnormalized. Then the argument I presented to you used basically scalar values for the states. In reality, the states are in the Monte Carlo, in the variation of Monte Carlo, are electron positions. Okay, so those are 3n coordinates. All right. So I simplified the metropolis algorithm because I used the scalar states, but states are more often they are not scalar quantities. They are defined by a vector. Okay, a state is defined by a vector. So in the case the state is defined by a vector, the move should be done either on a single component of the vector, and so I move sequentially component by component, or I can do a global move where I move all components at a time. Okay, and so you can have different evolutions whether you choose to do a single component move or a multi-component move. Yeah, so a general rule is that I should define this interval delta, right? This homogeneous box where I propose the new move. And so what is the best value of delta for the new move to be proposed? The general rule, I mean, which is sort of dictated by experience, is this 50% of acceptance, which defines the best delta. So this delta will affect how often I accept or reject the new move. Okay, so if I move too far from a thermalized state Sn, for instance, if I move too far, I will easily reject the new move if it's basically too distant from the actual path. So so this delta value will affect the acceptance rate of the new Sn plus 1. And delta should be set in general such that the acceptance rate of the proposed move will be around 50%. Okay, so now it's time to basically apply this to our initial goal, the one I presented you, I think 2 hours ago. So the goal is to compute the expectation value of H over psi. Okay?
Michele?
Yes?
Since there was a question, maybe we can take it now before you...
Okay, so let me see.
Start. So Samuel, if you can unmute and you want to ask this, feel free.
You prefer the question live?
Yeah, why not? Yes.
Sure. So thanks for the presentation. No, I was just wondering if a formal connection can be made, you know, between this rejection method and this metropolis algorithm. So in principle, if you sort of account for the number of time you reject with the, you know, the rejection method, I guess you can make a connection between the two. Is there such a connection, or is it like the position of the time you reject is important or is taken into account as well, or only the number of time?
So I don't understand the question. Since I don't understand what you mean by projection, the projection algorithm.
The rejection.
So the rejection algorithm. So the question is whether this rejection depends also, you're saying, on the position S of n. Could you repeat the question again? So it was not clear to me.
So in the rejection method, if
in the rejection,
given y you reject, then you lose the information.
Yes,
but let's say if I was keeping this information, so I was just weighting the state by the number of time the Y was rejected, would that be formally equivalent to the Metropolis algorithm, or the, let's say, the position in the chain in which I take the same state as the previous one, which is the same as rejecting? Does that position matter? And if it doesn't, I guess you have a perfect one-to-one correspondence.
No, that's the point, right? So you don't have this one-to-one correspondence because in the dumb rejection method, that's why I didn't answer your question, because we have two rejections. The rejection method, which was introduced as an example before, and the rejection step of the Metropolis algorithm. So in the dumb algorithm before, you can't keep the rejected state. Okay, so you can't keep the previous because there is in that previous algorithm there is no notion of chain. You see, there is no notion of chain. It's just drawing, if you like, random numbers on a box and partitioning the box, if you like, in white and black regions, and say the black regions are the one which are of interest for me because the black regions represent the probability distribution back to sample, and the white regions are basically wasted. So there is no notion of memory in that process. It's just the notion of falling in white on black regions. Okay, in the previous rejection algorithm.
No, I understood that.
While the improvement with respect to the previous rejection algorithm is that now I define a dynamics, if you like. I define a dynamics where if the evolution keeps the state to be the same, it means that that state is statistically important to sample the final pi. Okay, so there is no one-to-one correspondence.
My question was: is there a way to improve the rejection method by just weighting it such that there is a one-to-one correspondence? Of course, if you don't weight it, I understood correctly. I mean, I understood what you meant. My question was: is there a way to modify the rejection method to take that into account? But okay, thank you.
I think you can exploit, for instance, some symmetry. So what you can do in the rejection method, so you can exploit some symmetry of the integrand. So, for instance, imagine that you are sampling, for instance, I don't know, the area of a circle. Okay, and so you can exploit the symmetry of the circle to map, to reduce basically the target region where you draw your points. In that case, you accelerate somehow the convergence of the rejection method. So by exploiting the symmetry of the integrand, it's a sort of weighting it, right, in a proper way. So in this case, you can improve the rejection method by exploiting the symmetries of the integrand, for sure. Beyond that, I think you should really switch to the other paradigm. Yes. Okay.
Okay. Thank you.
Thank you for the question. Okay. So I have also some question. Okay. Another. Okay. Okay. So let's move on. So okay, good. All right, so now we are back to the problem of computing this expectation value for the Hamiltonian on the wave function psi. So again, the wave function form has been introduced in a very general way with just of factor plus the antisymmetric part. So Sandro tomorrow will explain to you much better, will explain period to you the form of the wave function. Now, for our purposes, for today's purposes, we'd like to find the formal way of evaluating this quantum value. Okay, and so let's write this explicitly. So psi h psi as integral over dr, where now r are the states. We're talking about S now have, if you like, a physical meaning. So these states S become the actual electron positions in the Cartesian space. And psi h psi is exactly psi star r h psi r, and that's the norm in the denominator. Okay. So now I can. So in order to apply the stochastic integration method, as I told you, I should be able to split the integrand into a product of a probability density pi of r times a function which in this case is local in R. Okay, so how can I handle this? How can I get to this form pi times O, if you remember the formula I presented you for the stochastic integration? So now I can apply, so maybe I can switch to the tablet again. Okay. Okay, so I have to compute this psi h psi over psi, the norm psi square. So this is written again as a multidimensional integral, where now R are 3n dimensional vectors defining the position of the electrons in the Cartesian space. Okay, so that's psi star h psi of R divided by the integral dr prime psi of R modulus squared, psi r prime modulus squared. Okay. Okay, now I had to play a little bit with the numerator. So here I introduce basically, if you like, a resolution of the identity, which in this case is very trivial. So here I multiply and divide by psi of R. Okay, that's equal to 1, right? So by introducing this resolution of the identity, okay, I end up with this form here. So psi star of R times my psi of R, and then I have this h of psi of R divided by psi of R. Okay, and divided all of this divided by the normalization. Okay, and so then I realized that that this one is positive definite. Okay, because that's exactly psi of R modulus square. And that's exactly my target, right? So I wanted to find the product of a pi function, positive definite, times a function whose sign can change. And the other function is this one. Okay, I can call it. It's called local energy by definition. Okay. This is the local energy. So psi, h psi over psi is the local energy. And so at the end, I end up with this form here. So my quantum expectation value of the Hamiltonian is equal to the integral over dr of pi of r times the local energy EL of r, where now again pi of r is my is defined as psi modulus squared normalized. Okay. So I've been able to recast the integral in a manageable form for the stochastic integration. And so here I introduce a very important quantity, okay? So the local energy. So local energy has a specific, very important role in any Monte Carlo algorithm we're talking about today and also in this week. And so at the end, the quantum expectation value in the stochastic approach for the integral is rewritten in terms of a sum, the average over m points of the local energy, EL, computed on Ri, where Ri are distributed according to pi of r, and pi of r is psi modulus squared normalized. Okay, so the quantum energy is the stochastic is given by the stochastic integration as the sample average of the local energy on points distributed according to psi modulus squared. Now, to make this robust and to provide reliable energies, I should be able to compute good means and good error bars. Okay, because if I provide a stochastic estimate of the true average, EVMC, I should provide both my best sample mean and also my error bar. Without error bar, if you like, my sample mean is meaningless. Okay, I should always provide error bar together with sample mean to determine how far my stochastic estimate of the true mean is far from it. Okay, that's a very important point. In Quantum Monte Carlo, in general Monte Carlo, the error bar has a major importance. A sample mean without error bar is meaningless because it doesn't tell me anything about the true average. Okay, only thanks to the error bar I can know that the true average will lie within the range around my best estimate. Okay, so now how to compute the, first of all, how can compute good averages and how can compute good error bars, okay? So now we should have a look at distribution of my sample means around the true mean. And so let's say I would like to evaluate the true mean. The true mean is this one, okay? It's the stochastic rewriting of my integrand as a pi times O, and that's basically it's done, if you like, on an infinitely dense sample size. So you can assume that this one is the true mean formally written, okay? With Monte Carlo, I draw a chain S1 Sm. So I draw a sample, stochastic sample of m elements, and my integral is written as the sum over this over OI computed over these elements. It's the average of OI computed over these elements. And that's the sample mean, okay? So we have now the true mean, which is this one at the top of the slide, and the sample mean, which is the average over my OIs computed over SIs. Now, the sample mean is an unbiased estimator of the true mean. Okay, so it means that the average of the sample means is equal to the true mean. All right, and in the case of a large elements, large sample size m. For the large numbers, the actual sample mean will converge to the true mean. So for m equal to infinity, for m tending to infinity, the sample mean will be equal to the true mean. But in the case m is finite, how the sample mean is distributed around the true mean, okay? And so in the case of m finite, we can apply the central limit theorem. So the central limit theorem states that having a sequence of m independent random variables sampled from a generic density function, and this probability density function has a finite expectation value mu and the variance sigma square. So the central limit theorem states that as the sample size m increases, the sample averages computed thanks to these sample elements S1, Sm, the sample averages of these random variables approaches the true expectation value mu, okay, and the sample averages for large M are distributed around the true expectation value mu in a Gaussian way, okay? In a Gaussian way, so according to a normal distribution, so another way of saying in a Gaussian way, with mean, the true mean, and variance, the variance of the underlying probability density from where the sequence has been drawn, divided by n, where m is the size of the sample. So the sample averages are distributed around the true mean in a normal way, with the variance, which is the variance of the initial distribution from where these points are drawn, divided by n. So that's a very important result, okay? Because the point is that given these, there are basically there are two major outcomes. The first one is that the way the sample mean is distributed is always normal, Gaussian, independently of the original distribution of, for instance, the local energies. So the local energies can be distributed in whatever way. Their average will be Gaussian distributed around the true average. Okay, so that's, the power of this is also the independence with respect to the original distribution. And the other power of this is that the variance is Gaussian around the true mean. And so it means that I can define a statistical error because I know how these means are distributed according to the true one. Okay, so I can define a statistical error on my sample mean. And the statistical error is the square root of the variance, which depends on the variance of the original distribution from where the energies or the random numbers are sampled, divided by n. And so here, this theorem tells me that the error of my stochastic integration goes like 1 over square root of m. So the important property which basically makes the stochastic integration, if you like, winner with respect to other approaches is a consequence of the central limit theorem. Okay, so now I'd like to compute now, to estimate the error of my sample mean. So how to do
Michele, sorry,
yes?
just to say that we are about 12:30. So I mean, since
so we started 10 minutes later, so I'm expected to finish in 5 minutes.
Okay.
It's okay. Okay. So to give an estimate of the statistical error, I should compute how the variance. How this sample mean is distributed around the true mean, okay? And so the variance of this is this quantity, okay? Now, if I plug the definition of the sample mean into this relation here, I'll find that the variance of the sample mean is takes this form here, okay? And this form is quite, I would say, a little bit at the first sight, quite complicated because it involves what is called the autocorrelation function, okay? Which is the correlation between the sample mean computed at the time s and the sample mean computed at time s plus t. Okay, but by time, I mean the time here is a jargon, and it's basically the chain position, if you like. So it's the index in the chain evolution. Okay. Now, of course, by definition, if t equals 0, this is exactly the definition of the variance of the true mean. And so by approximating, by extending the range of, the finite range, of course, because I have finite sample size of the correlation function, I can write the variance of the sample mean in this way. And then I can recast this double sum into the product of the true mean variance, the variance of the true mean here, times tau divided by m. This tau is the integrated correlation time defined here, okay, and tells me how the variance of the sample mean, the one I'm accessing numerically, depends on the variance of the true mean through the correlation in the Markov chain. So Markov chain leads to some autocorrelation between the members, and also I have again this factor 1 over m, which leads to the 1 over square root of m scaling of the error for stochastic integration. so I don't want to use this formula here. So you see that to get a good estimate of the variance of the sample mean, I should estimate the autocorrelation time, which is something I don't want to do. I don't want to do because it's sort of I mean, it's more cumbersome than computing this in another way. So I'm going to explain you what is the other way which is used, much more used to compute the variance of the sample mean. Okay, so I'd like to avoid to compute autocorrelation functions, and so the way used most frequently to compute the variance of the sample mean is the block average. Okay, so I split my sample size into n blocks. Okay, and so now each block let's say has nb italic nb members, and so the full size m is equal to the number of blocks times the number of members per block, and I compute the mean for each block. So the total mean, the run mean is the mean over the estimates for the block mean. Okay, but now what is the advantage of splitting now the sample size, the sample into blocks? If the block size is larger than the autocorrelation time tau, I can take these block means as statistically independent. Okay, and so then I can compute the variance over the sample mean by using the usual Gaussian form, Gaussian expression. So the variance of the mean is obtained as the evaluation of the variance for the blocks here. Okay, and so this estimate of the variance using the block averages, where now this OBI is the average of each, it's the mean of each block, and O bar is the full mean. So the variance using the block average for the block size larger than autocorrelation time, and for a number of blocks sufficiently large as well, will approach the variance of the sample mean. Okay, so so it's a way to incorporate automatically the autocorrelation time, which will affect the average of my stochastic, the variance of my stochastic averages. Okay, so I recall again for the last time the variation Monte Carlo approach, where I compute the variational energy of H or the wave function psi. So it's the expression value of H over the wave function psi. And so I have now a way to compute both averages and variances. And so I'm happy. And I can provide very reliable energy means and energy variances. So I just basically, it's recalling the Metropolis algorithm converted, applied to the specific case of variation of Monte Carlo, where now the states S are nothing else than the electron position R, which are 3 n-dimensional vectors. Everything goes in the same way, except that the states are now the electronic positions. And the target probability pi is the normalized, well, normalized, but this can be taken also unnormalized, because we have seen that in the Metropolis algorithm, pi doesn't need to be normalized. So my pi is psi modulus squared, okay? And so this is the last slide for today's lecture. We have talked about the variance of the sample and the variance of the sample averages. So if we take now the variance of the true mean, which is our goal, to get the actual true energy, the true expectation value of the Hamiltonian, the variance of the energy of my wave function is given by this relation. Okay, so and this relation tells you about an important property of the variational Monte Carlo algorithm. Okay, so it tells you that if psi is an eigenstate of H, in that case, the variance of the true mean, the true energy, is 0. Okay, and I'm going to show you just in a second. If the variance of the true energy, true average energy, is 0, it means that the error bar of my estimated mean is also 0. Okay, because it goes like the square root of the variance of the true average divided by square root of m. So it means that the closer the ansatz, the wave function psi, to the ground state or to an eigenstate, the faster is the convergence of the Monte Carlo error with a number of samples m. And in particular, for the exact eigenstate of H, the variance of my sample mean is 0. Okay, and why is that? And conclude with this very easy proof. Why is that? Because if you compute the local energy, so again, so we have seen that the expectation value of the Hamiltonian on the wave function psi, so the energy of the wave function, is written as 1 over m sum over configuration Ri of the local energy E of L computed at Ri, where Ri are distributed according to psi modulo squared. Okay. Now, what is the local energy? By definition, was H psi of R divided by psi of R. In a case of an eigenstate, what does it mean? For an eigenstate, H psi of R is equal to the eigenvalue times psi of R, if psi is eigenstate. Okay? And so if now I plug this eigensolution to my local energy, I get that H of psi of R is equal to E, the eigenvalue, times psi of R, divided by psi of R. Okay, and so this real number, so this goes away, this simplifies, And so the local energy is equal to the eigenenergy for all R. Okay, so for all points, the local energy has the same value, is a constant. Okay, and so it means that the variance of my energy is equal to 0 because it doesn't fluctuate at all. Okay, and so that's an extremely important property of the variation Monte Carlo algorithm, because if my trial wave function, if my guess for the ground state or for an eigenstate, an excited state of the Hamiltonian is close enough to the true eigenstate, in that case, my estimate of the energy and also other physical properties will have a very small error bar, and the algorithm will be extremely efficient to evaluate these properties, these quantum expectation values. And so then tomorrow, Sandro will explain to you how to devise very good variational wave functions such that the variance of these wave functions is small enough to be extremely well performing to compute quantum averages. And with that, I conclude today's lecture.
Thank you, Michele, and thank you all for staying a bit longer. So I suggest now we stop for a lunch break. And so the program is to reconvene at 1:30. Not sure if you're flexible on this. There will be an hour lecture by Kosuke Nakano, more or less. So, and then we'll start at 2:30 with the hands-on tutorials for some of you. So I would suggest to reconvene at 1:30 and try to be on time. So if you can have a quicker lunch, probably this would help the overall scheduling of the afternoon.
Okay, sounds good.
Yeah. So again, feel free to leave your Zoom there, or reconnect as you like. We'll stop the recording now and we'll restart it after lunch. You'll meet my colleague Jacopo that will open the Zoom. We'll guide you, but then Kosuke, feel free to start with your lecture.
Sure.
Okay.
Sure. Recording. Okay, sure. The second one is, as I mentioned a bit, this TurboRVB calls implement a VMC algorithm based on the localized orbital. And the point is state-of-the-art optimization method we can write in the paper. So the optimization is very stable and efficient. Indeed, I think in the other QMC code, they do not usually optimize nodal surfaces, but in our code, we optimize the nodal surfaces by a very stable, efficient method, which usually leads to a better variational energy in general, and also improve the corresponding diffusion Monte Carlo energy. Okay, we will explain actually this diffusion Monte Carlo in day 4 by Professor Casula. And also another important point is that the TurboRVB can calculate atomic forces actually very efficiently based on the joint algorithmic differentiation. As a consequence, using TurboRVB, we can perform also structural optimization and Langevin molecular dynamics that I don't think can by other QMC code. Okay, so the final one is the code implements actually the lattice regularized diffusion Monte Carlo, which will be explained in day 4 in detail, but which is, let's say, more stable than the standard DMC algorithm. Okay, so and actually we recently actually until 2020 the TurboRVB also accepts only orthogonal brabes, for example, orthorhombic one, the tetrahedral cubic lattices. But recently we implemented also non-orthogonal brabes, such as triclinic and hexagonal. So now TurboRVB accepts all the brabe lattices, so very generalized so far. So actually, indeed, the detail of the implementation has not been published yet. It will be published in the near future. So, okay. So, and so let me skip this one. Okay, so, and then TurboGenius, as I told you, this is a very important progress in our TurboRVB code. Although we are now preparing for the publication. Okay, this is as I told you, the Python-based wrapper to make it very easy, much easier to handle. You know, generating input, for example, analyzing output of Quantum Monte Carlo code, as shown in the hands-on session. Oh, okay. So let's see. So the TurboRVB works like this one. Genius works like this one. So in so this is very complicated actually process to generate the wave function, calculate VMs, and so on. So, for example, when preparing input file for the TurboRVB, we should edit the make floating input like by hand and prepare for basis set and some the atomic position and so on. And so to TurboGenius makes actually automatically generate the structure. The input files for VMs that make generating a function calculation. Okay, you just by typing like this one. Okay, in the tutorial session we will explain in detail. So for student, this explanation actually the explanation in this tutorial too much is concrete, specific for the practical aspect, right? Sorry for the student, they are not selected for the tutorial session. But I believe this information, it will be also very useful for you. Oh, okay. Oh. Let me see. Oh, why this one? Okay. So, and also several students have already asked me the important question: where TurboRVB can be downloaded and TurboGenius can be downloaded from. Okay, we as Professor Sandro mentioned, this is for time being TurboRVB and TurboGenius are in-house codes. So please do not distribute to the public. But within a couple of years, all the code will be public under an appropriate license. Though we are still discussing what license is appropriate. But anyway, so if you want to download it, would you send a request to Professor Sorella? So maybe we can give a permission to you, and you can download it from the GitLab server and to compile it on your local or your cluster machine. Okay, so this is the specific. Okay, and also we have already sent an invitation to this Slack channel. Okay, this will be public, so if you please do not submit the research project related questions on this Slack channel. Okay, if this will be public, and also not only for the student in this summer school, but also maybe for the users of TurboRVB in the future. And also, if you find some bugs or you have some open question, please post here. So we are going to make more specific channels here. So depending on your question, you will choose an appropriate channel and post it. Okay. So and we are now preparing also user guides, which include user manuals and tutorials, and also developer manuals. Sorry about that. This is not completed yet, but at least, so we actually welcome all contributors welcome to to compose this user guides. Okay, they are composed by Sphinx, so let's say so text-based, so which are very easy to compose and edit it. So, and also all the tutorials in this summer school is also included here. So after this summer school, once you can download TurboRVB from the GitLab server and compile it on your local machine or cluster machine, you can also trace all the tutorials in the summer school from citing summer school from this user manual, this tutorial section, section. Okay. And yes, so if you want to see the user guide, okay, and if you want to see the user guide, would you tell us? I will give the permission to git pull this this repository. Okay, so for the student who will join this tutorial hands-on session, no problem. You can on your local computer, so you can download the tutorials from Marconi 100 by this command, as I have already sent I have already posted to the Slack channel. Okay, you can check it. And sorry if someone is interested in the compilation of TurboRVB on their local machine. So I tell you how to compile TurboRVB on your local machine. Okay, we have two options to compile TurboRVB on the machine, but the point is, sorry, we are now refactoring the modern CMake method. So would you use legacy make for compiling TurboRVB? So first, there are a lot of templates for make file in the config directory in TurboRVB the repository. So you can first copy config make, for example, make Marconi 100 to make inch. Okay, and then you should also copy a make text file. This is saved in as here as src make text standard to copy src make text, and then you can compile TurboRVB by make all or make all MPI. Okay, so this is very simple, but if you have some trouble, would you tell me, or would you post some? Would you post to the Slack channel? Okay, we will help you with compiling TurboRVB on your local machine or cluster machines. Okay, and then we recommend that you should test the compiled binary on your machine whenever you compile TurboRVB on a new machine. Actually, we have already implemented a module to check if the compilation is successful or not. By go to test directory and you can run job check serial.sh, and this compares with your output with the previous output, reference output that we have already prepared. So if you do not, so here, for example, the difference between the previous one and the reference one, your output. Okay, if there is a difference, maybe you can see, you may see warnings, a lot of warnings here. So if you find some warnings, it means that your compilation option is wrong, or something like that. So so every time you compile TurboRVB on your machine, I recommend you should do this job check serial.sh. Oh, by the way, you do in the summer, sorry, the hands-on session, we have already compiled the TurboRVB on Marconi 100. So you do not have to do that by yourself. You can just refer to the compiled TurboRVB to do tutorial session, as I said. See. Okay, and also TurboGenius it's very easy to install. You can go to TurboGenius directory and you can do pip install, and that's all. So It's very easy to install. Sorry, this is I have explained the structure of TurboRVB. So let me introduce. So next, let me talk about the more general introduction of TurboRVB. Not more general. Let's see, more. How can I say? So the procedure of workflow of the TurboRVB, the web function representation and built-in DFT code. Okay, first the general introduction. Okay, the procedure let me clarify the procedure. Okay, the procedure in Quantum Monte Carlo method, not only in TurboRVB but also in other QMC code. First, we should prepare atomic positions, also the basis set and pseudo potentials. Then, first of all, we should estimate a good initial guess using DFT or wave function theory calculation. Actually, before, so we do not go directly to the QMC calculation, but first we should generate the initial guess using DFT or let's say DFT calculation, such using quantum espresso, Gaussian, or also PySCF, whatever. And using the obtained one particle wave functions, we do quantum Monte Carlo calculation as let's say as a post processes. And then finally we can get many-body wave function and its energies and forces and so etc. that we are interested in. Okay, so more detail in TurboRVB, the procedure like that. So which is a bit complicated. Okay, let me explain. First, we should prepare structure and basis set. Actually, we should prepare an input file including the structure and basis set informations, which can be done make for 10x in TurboRVB. And once we prepare the file, the input file, including structure and the basis information, we do a DFT calculation to, as I told you, to initialize, to obtain a reasonable initial wave function. In TurboRVB, this is done by our built-in code, called TREX. I'll explain why we employ the built-in code later, okay? And after initializing wave function using our DFT code, we can optimize the wave function. We can find the good variational parameter, a good variational parameter set by optimizing the variational parameters included in the wave function. And then finally, we can using the optimized wave function, we can do a VMC run to estimate the wave function, the energy or forces, etc. Okay, so if we can also do diffusion Monte Carlo calculation, which is much more exact compared with the VMC calculations. Okay, these three calculations, quantum Monte Carlo calculations, can be done in TurboRVB, TurboRVBX. Actually, there are three main binaries in TurboRVB. Okay. So in the hands-on session, we will do make for 10x and prep x in day 1, and in day 2, we will optimize the wave function, starting from the obtained wave function. Okay, and day 3 we will do VMC run, and day 4 we will do LLVMC with optimized wave function. Okay, so we have not explained the detailed VMC optimization and LLVMC. So this will be talked by Professor Sorella, maybe, and Michele Casula tomorrow or day after tomorrow. Okay, so today in the hands-on session, we will prepare input file, and also we will do DFT calculation for getting reasonable initial wave function for VMC calculation and the DMC calculations. Okay. Is it okay? Okay, next I will talk about the wave function representation in TurboRVB. Okay, so in TurboRVB, all the information about the wave function, including the structure information, is written in Fort10 file, which is, sorry, this is the default name of the Fort1 output, but this is the most fundamental the file in TurboRVB. Okay, so the procedure like this one. So first we should prepare structure information, including the valence electrons and the charges and X, Y, Z Cartesian positions. And also we should prepare basis set the information. I'll explain it later in detail. And we can prepare make 14 input file like this one. Okay, and using make 14x, we can generate a wave function file. This is called Fort10. Okay, so I do not explain detail, but okay, as I told you, all the information except for pseudo potential information is included in a single file named Fort10 here, like this one. Okay, so I will not explain detail, but let's see. In the header of the Fort10, there are a lot of important information. Okay, like this one. For example, here NEL-up. NEL-up is the number of spin-up electrons in the system, and also NEL here NEL. NEL is the total number of electrons in the system, and here one means ion. The number of nuclei in the system, like this one. So by seeing the header of the Fort10 file, you can check if the Fort10 file is consistent with what you expect. Okay. Also, there are total number of Jastrow parameters like this. So, I do not explain this one. So. The header file, you can see all a lot of information of the Fort10 file. Okay, so and then in ion coordinate tag section, you can see n is the atomic number. Oh, sorry, this is opposite. Sorry, n is the valence number of valence electrons. Okay, and n is atomic number, and position, Cartesian position, x and y and z. You can see the unit is Bohr. Okay. Let me see. So, and sorry, this day 2, Professor Sorella explained what answered actually the parameterization of the many body wave function in detail. So here I do not explain detail. So, but anyway, let me explain the point. The TurboRVB employs a many body wave function ansatz that can be written as a product, as Professor Casula explained in this morning. The wave function is generally described by the two terms. One is antisymmetric part, and the other one is Jastrow factors. Okay, and Jastrow, the antisymmetric part is usually written by expressed by determinant, and here GS is so-called pairing function here, and Jastrow part also like Jastrow part composed from 3 terms, J1 and J2 and J3 typically, and they are let's see, parameterized like this one. Okay. I do not explain detail, but the point is that this antisymmetric part is parameterized. The pairing function is usually parameterized by one particle orbitals. This is called basis set, for example, in the quantum chemistry, the community. Okay, and also the Jastrow part are also composed, the parameterized used by this chi. One particle orbitals, typically Gaussian. We can choose also the Slater basis sets. So, okay, so we should, in the input file, input file, we should specify what basis set is used for the determinant part or also for the just or part. Okay. So in make for 10, in TurboRVB, we should put what basis set is used, okay, here, like this one. And this is Z. Gaussian is like this one, right? It's exponential minus Z, exponential minus Z R squared. This is Gaussian orbital, okay? We can specify what Z here, and also Gaussian orbital has the angular momentum, so we can also specify the shell codes, like S orbital. In TurboRVB, 16 means S orbital, 13.6 is P orbital, 16.8 D orbital. You should remember this one to use TurboRVB. Sorry, this is not SPD, but we should specify the numbers, okay, here. So this means that this is S orbital with Z equals 0.5. And this orbital means P orbital with Z equal 1.0, okay? So, and in practice, one important question is that how to choose the basis set in quantum Monte Carlo calculation, okay? So for open systems, we can use a provided basis set as it is. For example, there are two very famous databases for quantum Monte Carlo calculations. Okay, they provide pseudo potentials with appropriate basis set from on their websites. Okay, so we can take their exponents and pseudo potentials and combine them in our make for 10 input. Okay, and for all electrons, okay, we can also take the provided basis set. But so, for example, one of the famous basis set databases is basis set exchange. I think you may know because this is used for the quantum chemistry calculations, right? But the point is, we maybe tomorrow's Professor Sorella will explain this one. In TurboRVB, in quantum Monte Carlo calculation, we should satisfy the cusp condition to avoid numerical instabilities in quantum Monte Carlo calculation. So in TurboRVB, we add to satisfy the cusp condition, we add just or factor to the one particle, or also one particle wave function, even at the DFT level. Okay, so it means that here in the vicinity of nuclei, we do not have to put the larger exponent provided in the basis set exchange. Okay, so it is better to cut the several largest exponent for all electron calculation. Okay, for pseudopotential calculations, this is not necessary because in general pseudopotential with the pseudopotential calculation, the cusp condition is not necessary to be satisfied. For electron ions, cusp condition is not necessary to be satisfied. Okay, for electron calculation, we usually take basis set from this basis set exchange and cut the largest exponent. Okay, and TurboRVB employed for the periodic boundary condition calculations. The situation is more complicated. Okay, TurboRVB is employed the called crystal periodic basis for PBC calculations, like this one. So localized basis set multiplied by plane wave is exponential form. So unfortunately, a provided basis set for open systems are very redundant for periodic cases. So if we employ the provided basis set as it is, the calculations would be very unstable, the DFT calculation. So we recommend that one should cut several smaller exponents in this case, typically smaller than 0.10, which could alleviate the redundancy. So also for the all electron calculation, we can take the provided basis set for open systems from, for example, as I told you, from a basis set exchange, but we should cut. It is better to cut a smaller exponent, typically smaller than 0.10, to avoid numerical instability. Okay. So, and we should explain, okay, I should explain built-in DFT code. As I told you, TurboRVB employs our built-in DFT code, own DFT code. Actually, this is different from other QMC code, I think. So, for example, in Casino, as far as I remember, they generate the procedure like this one, right? So, first we should generate the reasonable trial wave function for, sorry, here. Oh, sorry, missed the slide. So, okay, in quantum Monte Carlo calculation, first, as I told you, we should prepare a trial function using DFT calculation. And the other QMC codes, they generate the trial function using commercial or free, so let's say, very established QMC code, such as Gaussian or quantum espresso. And then they convert the obtained DFT wave function to QMC for the format suitable for their QMC code. But in TurboRVB, as mentioned before, we employ the modified Gaussian orbital is used, right? The Gaussian multiplied by Jastrow factor. So, which means that we cannot exploit the analytical X integration, even though we employ the Gaussian primitive orbitals. Okay, this is, as you may know, this is one of the advantages of the Gaussian primitive orbitals for the quantum chemistry, the DFT calculation, right? But we cannot exploit this feature since we modified the one particle wave function, okay, the orbital, okay. And also another problem that we, as I told you, TurboRVB, we employ the crystal basis for the crystal basis plus cusp condition with the cusp condition for PBC cases, right? So in this case, it is Professor Sorella confirmed that I think 10 years ago, it is not possible to convert wave function, plane wave based DFT calculation to our basis set. It was not satisfactory. So satisfactory. So that's why we to prepare our good initial wave function for also for the periodic boundary condition calculations. We need our built-in DFT code. That's why we implemented our built-in code. Okay, so okay, like this one. So first, okay, let me mind this one. So in first day and day one, we will make for 10x and PEPX to prepare an initial guess for the QMC calculations. Okay, so. Maybe the detail will be explained tomorrow. So, but as I told you, TurboRVB employs the Jastrow antisymmetric geminal power with geminal powers for the determinant antisymmetric part, which is described by the pairing of the one particle wave orbitals, okay? So, but this does not, so DFT calculation works only with the Slater determinant. So we should, in TurboRVB, we should add the molecular orbitals to this JAGP wave function, the template. So that's why here you can see the procedure is a bit complicated. First, we should prepare 410 file. Actually, this is the template of AGP function that cannot be that PrepX does not accept. Okay, so first to do the DFT calculation, we should convert the JAGP template to JSD type using this convert fault mode program. Okay, so that's why this is a bit complicated. And then after this, we can convert the wave function as we want to. For example, more flexible ansatz. Okay, so in 410, after adding molecular orbitals, you can see this number, 100,000. If you find 100,000 in 410, it means that, okay, this wave function includes molecular orbitals. Okay, we the hands-on session, we can see this wave function, this molecular orbitals in 410 file. Okay, so you have time, right? So in this is a typical DFT input, prep input in TurboRVB. Actually, the very input is very simple. The only important part is two. One is the molecular tab, the other one DFT tab. Okay, this DFT grid I'll explain later. Okay, in DFT nameless section, we can put the typical DFT parameters as in the quantum espresso Gaussian. Okay, this is max iter, so max number of iteration, the self-consistent one. And also we can put IPS DFT tolerance in the convergence of the total energy. Okay, also we can put mixing and also mixing. And the one important things I should tell you is that the TurboRVB implements only LDA and LSDA functionals at present. So we can choose one of them. Actually, for the non-magnetic, non-spin polarized calculation, it's better to choose one. And for spin polarized calculation, we should choose 4. Okay. And this is opt-awk. The other one, another important option is opt-awk. So 0 means we use fixed occupation. And 1 is use a smearing film distribution, which is suitable for metallic calculation. Okay. So if you put to 0 here, you should specify the number of occupations that read from here. For example, in this case, this is sorry, which one? Okay, so in this case, the system has 6 electrons. Okay, and unpolarized. So that's why we should put 2, 2, 2. Each orbital is occupied by 2 electrons. Okay, we should put like this. If you put 1, I mean, using a smearing frame distribution, you do not have to put occupations here. Okay. And so in TurboRVB, as the most practically important parameters is box and mesh sizes are so important obtaining, let's say, a result consistent with the other quantum chemistry or quantum chemistry DFT codes. Okay, so Hamiltonian in TurboRVB is evaluated on a mesh. Okay, this is the size of mesh is specified by A here, A, X, and AY, and AZ. Okay, and the box size for open system is specified in A multiplied by N. Here we can put N. So the point is we should choose the appropriate N, A, small enough A, depending on the system. Okay, if we use pseudo potentials, to our experience, A equal 1.0 Bohr is small enough. Okay, but for on all electron calculations, we should need to much smaller grid to get a converged result. So but in principle, it is better to check the convergence before proceeding with the VMC and DMC calculations. If one can use from the commercial DFT code Gaussian, it is better to check the consistency between them. Okay, so and if you have for the open system, it is better to take, to our experience, L is about 20 Bohr is enough for get the converged result. Actually, it also depends on the system, so you can check the convergence before proceeding with VMC and DMC calculations. Okay, for LZ, the box size is set automatically for the cell lattice parameters for periodic system. So in periodic system, PVC calculations, you do not have to specify L, so in N only. You can specify you should specify A grid size. Okay, so as I told you, TurboRVB implements on the LDA and SDA functions. Okay, so this corresponds to SPL in Gaussian. So as I told you, I usually confirm if the prep TurboRVB DFT energy is consistent with the Gaussian or games result. Okay, as far as all parameters are the same. I mean, the basis set or pseudo potential parameters and also functional exchange correlation functions, they should give the same energy as written here. For example, recently have checked also this very big molecule, Gaussian Turbo DFT give an essential identical energies. Okay. And also we, for all electron calculation, we implemented the so-called double grid DFT calculation. So in the vicinity of nuclei, we should need more dense grid to describe the wave function more accurately, right? So if you turn on the double grid option in the simulation section, you can do this double grid DFT calculation, which helps us with getting a converged result for electron calculations more and more conveniently. Okay, so let me remind this one. So the day one, we are going to do, we are going to prepare a structure and the basis set using make for 10. Okay, and then using this one in detail, the generated wave function by this make for 10 is JAGP wave function, which is actually that are not accepted for DFT calculation in principle. So we should convert the wave AGP wave function to theta determinant wave function using convert fault mode.x. Okay, using this JSD wave function, we can do a DFT calculation using our built-in code prepx and get a reasonable initial wave function. And day 2 and day 3, we can do the VMC calculation or DMC calculation. Okay, so this is okay. So there are tutorials that we have prepared. We have prepared 3 tutorials. One is hydrogen dimer and the carbon 2 dimer. The other one is hydrogen 2 or graphene, which is their open boundary condition calculation. And this is a periodic boundary condition calculations. And so day 1, we will do this day 1 part, DFT part. Okay, so that's all. Sorry, maybe the explanation is a too bit practical, so maybe it's helpful for students who join the tutorial session. Okay, sorry. Okay, so sorry if you have some questions, would you tell us? Okay. Oh, sorry. Yeah, we have.
Yeah. Good afternoon. On the Zoom account, we don't have any questions posted.
Okay, but in the Slack channel, let's see. Is double Bluetooth false? No, we do not have any.
Kosuke, right now we received one question coming
Okay,
from
sure.
So the question is, does the double grid DFT is convenient for all type of chemical systems?
Yes. Oh, sorry. All type. What all type means? Would you tell me what all type means?
Maybe we can put.
Yes.
Kindly unmute your microphone so that you can verify your question. Thank you.
Sorry, I cannot. hear you clearly.
We have examples with fullerene or the thing molecular system like organic compounds or the use in your presentation is, but there are a lot of chemical systems. Does the double grid DFT are convenient to them to other chemical systems too?
Sorry, actually, I could not hear you clearly. So would you tell me again? Maybe due to the bad internet connection, I think.
Okay, I just feel a bit.
Oh, now I can. Yeah, now I can hear you clearly. Yes.
In your presentation, you use fullerene as an example, but there are other chemical systems too, such as polymers or organic compounds. My question is, does the systems too cycles? Thank you.
Yes. I think I think we can use the double grid system, but we should tune our parameters. Actually, the double grid system method has several hyperparameters, so which should depend on the chemical species. Okay, let's say. So if we want to use, for example, the double grid for much heavier atoms, you should you should increase the number of mesh grid in the vicinity of nuclei. There are several parameters included as related to this grid size or the region in which the double grid scheme is used. Yeah. So unfortunately, they are not automatically adjusted. So we should think about that by ourselves. This is, okay, maybe I cannot hear.
Okay, I think we can move on with the next question.
Okay.
If Ibrahim, you want to unmute yourself and ask your question. Ibrahim, are you there? Or okay.
Hello, can you hear me?
Yes, I can hear you.
You said previously that plane wave bases are not suitable as gas bases in QMC. Can you briefly explain why?
Oh no. So the plane wave bases can be used, let's say, in quantum Monte Carlo calculation. In detail, in other codes, they convert the plane wave function to blip wave function, and then they can proceed with VNC and DMC calculations. So plane wave is okay, acceptable for QMC calculation. But in our case, we use a crystal basis, which is a bit different from the plane wave, right? So the conversion was not successful as far as I understand. So yeah, plane wave is okay. It's also QMC calculation, but for our codes, they are not suitable. Does it work for you? Yeah, sure. Yeah, it's better.
Okay, if no one has any other question, also on Slack, I can see that there are no other questions. We can move on with the head zone. So thank you very much, everyone, to participate to the event, to the first day of the event. Now we will open the breakout rooms based on the tutor and their decision that they make this week. So thank you very much. And in order to participate to the breakout rooms, you have just to accept our invite. Okay. And I just wanted to add that it's going to be recorded hands-on. So for whoever is not going to participate to the hands-on, you can see the registration and the recordings after the event. Thank you very much.
I should go. Sorry. Sorry, I need 5 minutes to go up in my room.
Yeah, no problem, Sandro. I just start now the breakout rooms. So if you guys can just join. Also Kosuke, also Michele, if you want to join inside the breakout rooms, you can see that most of them are there. Okay.